All right. Good morning, everyone. Good morning. Good morning. As I was reminded today is Global Encryption Day, but it is not Global Decryption Day. So this is a one-way journey. And when we meet next time, we'll do the other half. All right. My name is Ron Petty, and I am one of the co-leads along with David Issa and our other co-lead, Andreas Vega, who is currently not here today, was here all up until today. So he's put in a lot of work. And our advisor, Boris Kirchhoff, who's also not here today, but will be online and will chime in as he finds I'm doing something incorrect. All right. So I'm going to talk a little bit about what Global Encryption Day is, who's the parties, what's the purpose, and then, of course, we'll get into our training. So Global Encryption Day is created by a group called the Global Encryption Coalition, which was spawned off from the Internet Society and many neighboring related topical companies made this group where the goal is to safeguard encryption. So there's many things that go into security, and encryption is arguably, if not the penultimate piece of security. It is very close to the most important part of being secure. And so making sure countries don't withdraw from these protective measures is part of the goal of the Global Encryption Coalition. You yourself can join. They have resources to learn. One of the resources is Global Encryption Day, which is why we're here today. We'll talk more about this in just a moment, but please check it out. They have a lot of resources, including training resources as well. Now, for the actual San Francisco event, so Global Encryption Day San Francisco is put on by two chapters of the professional society. So one, of course, being the Internet Society. So the Internet Society of San Francisco, we're the local chapter of the overall Internet Society, who we have, which we'll have in a moment come up, Charles Mock, who's on our board of trustees of our global organization. And then the local professional society, the chapter of the Association for Computing Machinery. So I happen to be a member of both. David is a member of both. Andreas is a member of both. And we hope everyone becomes a member of both. So the Internet Society is very action focused. So we try to help put on events like this. We also do a lot of grant work to help others. You can go to our website and check out all the various projects we've been working on. The ACM also is very active. So there's a global operation, but even our chapter is very active. So we have 2 to 3 meetings a month, usually down in the peninsula. Prior to COVID, we had more meetings up here in the East Bay, and we're trying to change that. That's part of why we're partnering here, is to bring more of this good stuff to San Francisco. So again, we would love you to join both. Internet Society is actually free, $20 for professionals for the chapter. And there's a variety of benefits that come with that. But the main thing is come to our meetings. Even if you don't join, enjoy the company, the camaraderie, learn all about tech. Our YouTube channels, there's hundreds of videos from all of our past meetings and presentations. So please check it out. A lot of good stuff is there. Additionally, we'll talk a little bit about our sponsors. So the training track today is from a company called RXM, of which I am an employee of. I'm a principal consultant at RXM, and my colleagues are here as well. And Chris, who is our lead trainer today, is going to talk for a moment about RXM and just tell you about what it is.
I have the live.
Okay.
Hey, everybody. Welcome folks online and everybody in the room. So RXM is a global cloud native and artificial intelligence consulting, training, and advisory firm. So we spend a lot of time in the cloud native space. So we'll do some of that today in the training. We'll deal with containers. So if it's an introduction to containers for you, then that's great. We'll expand your world in terms of containers. But a lot of the time we're going to spend today is dealing with software supply chain security, because it is one of the major threats for cloud native applications. So yeah, as a firm, we spend a lot of time with making sure that organizations' supply chains are secure, and helping them adopt new technologies like artificial intelligence and machine learning. And we've spent a lot of time in like the machine learning ops space recently. Thanks, Ron.
All right, thank you, Chris. I'd also like to introduce our other co-instructor, Christian Laksina.
Thanks, Ron. So my name is Christian Laksina. I am a cloud native DevOps engineer over with RxM. And I am also a trainer just like Chris and also just like Ron. And today I will be presenting the labs for all of you. So I'm going to be giving Chris a nice break from all the yapping and talking. So he will get and you'll get a chance to come with me to actually do a lot of these labs together. And it's definitely something that's always been my pleasure to do. And all right, thanks, Ron.
Thank you, Christian. All right, our other sponsors, Mazer 42 or M42. This is Andreas Vega, our co-leads for this event company. They specialize in advanced crypto platform tooling and evaluation. So this includes things as crazy as quantum encryption. So if you're really into it deep, M42 may be a place to check out. Additionally, we have Frontegg. So Frontegg, we'll see some slides here, is an advanced authentication user management platform for your SaaS. And so we'll see the slides coming up in just a moment. Lior, our sponsor at Frontegg, she'll be here later to talk a little bit more about Frontegg, and hopefully you'll take a look. We also have the Cloud Native Compute Foundation. So if you've heard of Kubernetes, that is the home of Kubernetes and many of those kinds of tools. And so we want to thank them for the marketing support of this event as well. All right, so again, Lior will be here later to talk about Frontegg, so I won't spoil her surprise. Again, a little bit of what we do at RxM, not just instruction, we also do consulting and advisory type work. A lot of AI, as you might guess lately. By the way, I should point out, if you are interested in any of our class, open enrollment classes, that's for 50% off. And we have many, many types of classes, not just Kubernetes, not just AI. So please take a look. We also will be giving out a couple of open enrollment for 100% off of these here at this event, and then over at the Thought Leadership track at Cloudflare. Again, the CNCF, we love these guys. All their plushies down here are from the CNCF. There's a whole lot of them, including Commander Cube. That's the Kubernetes mascot. Okay, again, M42, Miser 42. All right, we'll be getting it. Greg, we'll get into the groups in Zach just one moment. All right, so just a little more information, just so you can see the names here. Again, Global Encryption Day is a global event. Today is the official day for it. There's been events going on for over a month. We probably think going to hit 120 events around the world up until today. This is our attempt to do it justice and spread the word about encryption. So please, any feedback along the way, anyone here has experience in any of these tools and techniques and you want to share, we're all ears. We would love to hear about it. Again, this is by the chapters, and there's our names. Again, there's been prior events already. This has been going on for a few years, so you can check out the artifacts from those events as well. All right, next, I'd like to bring up one of our partners, our lead partner, the Internet Society. So if I can introduce Zach Taylor and Charles Muck to come talk a little bit about the society. We'll start with Zach, who is on the board of our local chapter.
Thank you so much, Ron. Good morning, everybody. I'm so excited for Global Encryption Day. Can I get a woo? Let's get it going today. This is fantastic. So as Ron mentioned, you know, the Internet Society is a major sponsor of this event. We're so excited to have you guys here. Just to let you know, the mission of the Internet Society is really important. You know, we really focus on the furtherance of the development and evolution and a free and open internet, which is so important globally for everybody across the world. Okay, and your local chapter works hard to align its mission with the global initiatives. Every year they come out with a large initiative, and we align with those goals and try to promote them in the San Francisco Bay Area and all throughout California. So it's a really exciting time. If you're not a member already, I implore you, join us. Come join the board. I'm a board member. We have a great time. We put on fantastic events. As you can see, this last year, we came out with 2 fantastic white papers. We sponsored some lectures on AI. It was a really gangbuster year, and we're hoping that you guys come out and do the same thing and join us. So, hey, let's have a great day to get together and really have some fun. Thank you, everybody. Ron.
Thank you, Zach. Next, I'd like to introduce Charles Muck, who's on the board of trustees of the Global Internet Society.
Thanks, Ron. I'm Charles, and my day job is actually a research scholar at the Cyber Policy Center at Stanford University. So I'm actually also, of course, as Ron said, I'm on the board of trustee of the Internet Society. The Internet Society was formed, almost 30 years ago by founders of the Internet, Windsurf, and a number of others, to really try to make sure the development of the Internet is going to be one that is safe, secure, and we want to connect the unconnected. So through the work of ISOC, Internet Society, and also our foundation, we want to connect those countries and people from places where they are not yet connected in order that they can receive the economic and social and educational benefits. At the same time, we support a whole number of standard organizations, like Internet Engineering Task Force and all the others. We work with them, we help support them financially and in terms of policy support, also working with governments all around the world to make sure that, the rules and regulations that affect the Internet and technology are going to be positive. So that's the work that we do. My journey with my chapter, when I first founded my chapter, more than almost 20 years ago in Hong Kong. And we actually now have more than 120 chapters all around the world, all continents, everywhere in the world. So wherever you're from, you probably find a chapter where you came from. But of course, you're now in San Francisco, and I hope that we will all join and support the work of the local chapter here in the SF Bay Area. And thank you so much to your team, Ron, for putting this together, and hope we will all have a great day here. And maybe some of you will go to the other venue later in the afternoon as well. So thank you very much.
Thank you, Charles. All right, next, I'd like to introduce Greg Weinstein of the Association for Computing Machinery.
Welcome, everybody. I'm Greg. I'm very pleased to see you all here, both in person and online. And thank you all for attending our event today. I just wanted to say a few words about the AC. Oh, first, I wanted to say about the Internet Society, how wonderful they are. If you did not see the I-50, the 50th anniversary of the Internet event that ACM and ISOC participated in, you can go to IEEE.tv and click on the I-50 link. Windsurf and many other luminaries spoke during that event, and we've got it all captured on video. And in fact, the local chapter of the ACM does that also, capture things on video, including today's event. ACM, the Association for Computing Machinery, back when it was founded just after World War II, is the official, principal, and largest international society for the advancement of computing, educational, technical, and professional. ACM does many activities, has more than 30 special interest groups, and has involved in some 70 scholarly and consumer publications for people in the field of computing. Practically every PhD in universities and in research labs are members of the ACM. You probably were members of an ACM student chapter while you were in college. We're the professional chapter for the Bay Area region, and we are 67 years old and still going strong. The San Francisco Bay Area ACM professional chapter does, I'd say over 25 events per year, many of them totally free of charge, most of them very convenient to public transportation and to Silicon Valley. So we encourage you to look at our meetup page, SFBay ACM, or go to sfbayacm.org to read more about us. I especially wanted to thank Ron over here for his excellent work in coordinating, organizing, and driving everything that's going on today. Thank you, Ron.
Thank you, Greg. Greg's the best. I hope to be like Greg when I grow up. All right. Also want to say thanks to our other chapter members who are here. We have Gustavo Ortega, who's our treasurer for the local Internet Society. With our volunteers, we have David, who's also a volunteer on these groups. We have Professor Catherine in the back, who's also thank you for coming. And we cannot forget our remote AV team of Carl and Bill. So Carl and Bill, take a bow. We appreciate you. Okay, again, we would love for you to join us. You know, our events are largely free. Sometimes we do fundraisers so we can actually keep it going, but mostly free. Again, lots of educational events for those, you know, I don't want to guide anyone wrong. ACM, lots of educational events, right? We're there to learn, meet people who create these things. And the Internet Society, we're really trying to, you know, provide that equitable access. And that means go get a grant, go buy equipment, go teach people. Like most of our events, or I should say grant work, has been done outside of San Francisco, right? So I should also mention to Tom Thorley, who might be joining us, we just launched the LA SoCal chapter of the Internet Society last month. So we've decided California is big enough that we took one of our board members, Tom, and launched him to Hollywood. And now we have a chapter there where they're going to hopefully focus on a lot of the key industries down there. So gaming, Hollywood, of course, or media, right? Things like that. Plus just it's a large city, right? Los Angeles and Riverside and everything around there, right? So there's plenty to do just in California, but we operate everywhere. Okay, this event, just to be clear, so there's no confusion, the Global Encryption Coalition is the ones who run Global Encryption Day as a general concern. They do not take direct donations, but the Internet Society does on their behalf. So if you wish to make a donation to support these kinds of events, again, we have over 100 this year around the world. We do get grants to help put on these events, so please, we'd appreciate anything. All right, here's our agenda, probably the reason everyone's excited. All right, so here at Google Community Space, which thank you, Juliana and team who are around the front. We really appreciate the space. So the training will be led by Chris and Christian. You could see the outline here. I'll let Chris get into that when he comes up. And then starting at 2 o'clock, the thought leadership will start. The main aspects of it will not start till after 4:30. So that'll give you time to go from here. It's a 20-minute walk, but of course, if you run, you can get there faster. Sorry, we're at 2 locations. We actually had a unified location. We lost it, had to split up, and hopefully not to any ill effect here. But we appreciate Google Community Space and Cloudflare for hosting this. And we also hope there's going to be a couple of panel discussions at the other site. And we really hope we get participants from the crowd to also participate, not just our esteemed experts. We want to really capture everyone's level of experience with encryption and related technologies. If you have any issues, you can email me. That's my email. I'm trying to stay up on it. If you got anything wrong or concerns, please just shoot me a message. Okay. I'll give you a moment to take a look here. So what is Global Encryption Day? Global Encryption Day is an annual event organized by the Global Encryption Coalition designed to raise awareness about the importance of encryption, protecting privacy, and securing digital communications. Brings together various stakeholders, including civil society organizations, technology companies, individuals, to advocate for strong encryption policies and practices. So that's the mission. Okay, so now, why? Anyone else have another reason to care about encryption? Or is that's probably the only one we need? Hackers, yes, hackers, evildoers, right? So there's the lead in. Okay, at this point, I'm going to turn it over to Chris to lead us at our training. So let's welcome Chris.
You want to just hand that up to him and we'll go from there.
You want me to leave it, or do you want to go back on the left leader?
I'm gonna move some of these
You want
these things around
want-
so we can have better view. So give me a moment. Okay, so if you've been to the GED website that Ron set up for the event here, you have access to the deck. But there's a QR code here if you want to scan that too. That's going to have all the slides. This is just a Google presentation that you get access to, so you can have access to the slides whenever. I believe it's open for sharing, so you should be good there. If you need any help during the day, Christian's going to be going around the room, or I'll be going around the room, and we'll help folks get set up. Each one of the stations here has, or each one of the seats has a small half sheet of paper for doing the lab work. And so it does have some instructions, but we'll also help folks get set up for doing the lab work. Before we get into any specifics on the lab that Christian will do. And if you need to email us for any reason, like Ron said, we're going to try and keep up on our email so that we can get folks help for this stuff. So we have 4 sections we're going to go through. We're just going to talk about cryptography to start with. And then there is a problem statement in that section about managing keys and how we can work around that. And so that's section 2. We talk about keyless cryptography and what that is, and some advancements in cryptography and managing keys. Then we'll move on to software supply chain security. As I mentioned, this is one of the major attack vectors in cloud native. So we want to have an understanding of how to secure our supply chains, especially as a developer of software. If you understand some of the advancements in this area, then it will help you in your career. And then we'll wrap up with some security frameworks. Really just gives us a chance to have a common language that we all can speak with these frameworks and discuss how we're consuming software securely, how we're producing software securely, those types of things. So we're going to start with cryptography and software development. So why do we need this? We talked about hackers, right? That was the first thing that came up when we're talking about losing data. Right? You can see the statistic on the bottom of this slide talking about the average cost per data breach in the United States is 9.48 million in 2023. This is up from 2022. Not that much, but over the years, if you were to look at statistics, the cost of data breaches have gone up year over year. This year, we're on track to be about the same, if not a little bit less for data breaches. Now, globally, it's lower. So in the United States, it's much higher per data breach. So globally, it's like about 4.5 million per data breach. But here in the United States, nearly 10 million per data breach. So it's a lot of financial responsibility on the line, right? These are expensive. We're talking about money and public trust because, of course, it's reputation on the line. So being able to encrypt communications, making sure that we're deploying software securely, consuming software securely, means that we, of course, don't lose the faith of our customers, and we avoid this type of monetary loss. So there are security risks inherent with cloud native applications. And so we want to build into our systems access controls, making sure that privacy is built into everything we do. You may have heard the term shift left, right? That's bringing security as far up the supply chain as possible so that we do these things securely. So some of the technology of cryptography include things like encryption, right? The making sure that we convert a plain text message into a cipher, which usually involves an algorithm and a key. And we'll talk a little bit about key management and some of the concerns around key management in this first section. This is our generated value that configures the algorithm and then allows us to both encode and decode the cipher. Public key infrastructure are policies, software, protocols that generate and distribute public and private keys. So when we talk about symmetric, asymmetric encryption, they both involve keys, and we need to be able to communicate those keys to different parties securely. Another concept here is cryptographic signing, right? We're going to provide guarantees around messages, right? So that when a message is sent, the identity of the sender can be guaranteed, that it is unaltered, right? That we don't have someone in the middle changing that message and then tricking the receiver. And then hash code here is a mathematical function that is applied to elements of a message so that we have a statistically unique code for that message. And the output of that is known as a digest. If you've used Git, then you've been introduced to this, whether you know it or not, because Git uses digests to indicate that a particular commit, for example, because it has a hash, is unique, right? Now, a lot of the technology around cryptography has to do with compute power, right? So interesting quote here from Edgar Allan Poe, right? That human ingenuity cannot concoct a cipher which human ingenuity cannot resolve. So oftentimes it's humans that can be the weak link, and we need to ever evolve cryptography in order to make it secure, right? And so Ron had mentioned, quantum computing. That's a big danger to cryptography because of the fact that ciphers are only as secure, and we'll have a slide on this in a moment, as compute power grows, then ciphers become weaker and weaker. And that's why if you had a cryptography algorithm from the 70s, for example, it's no longer valid because compute power is so powerful that it can be broken much quicker these days, right? So there's a couple different types of encryption. We have symmetric encryption and asymmetric encryption, just to cover kind of the differences and the pros and cons of each type. Again, each uses keys, right? We have a key to, in symmetric encryption, a key to encrypt and decrypt the message. So it's a shared key. But this means that you have peers where we're communicating securely, right? So on each side of this diagram here on the top right, we have a sender, we have a recipient. They're using the exact same key to encrypt the message and decrypt the message. The challenge with this is that we have to have some sort of secure technique in order to transmit that key, right? Because the key can be used to do both the encryption and the decryption. We have to have some existing secure channel in order to communicate that key between the two parties. The pros here are that the keys are shorter, the encryption and decryption is faster, but you have that challenge of sharing the key. Whereas with asymmetric encryption, you have a public key and a private key, where the sender of the message uses the private key to encrypt and then shares the public key widely. And so we don't require a secure communications channel to transmit that public key, because anyone can decrypt the message, but it guarantees that the holder of the private key was the only person that could have transmitted that message. And we know that we have a way to guarantee that that message has not been altered unless the private key gets compromised. And that's one of the risks here, is private key compromise. We have to make sure that we protect our keys. And again, we'll talk a little bit more about managing keys and some of the challenges toward the end of this section. Oftentimes these algorithms work in terms of a cipher. And so there are three types of ways that we work on messages. So we have block ciphers. This is the most common. This is where we have some amount of data, and we're going to encrypt that. So we know how much data we have. There's nothing in flight. Stream ciphers work through modes of operation and allow us to encrypt data as it's flowing. And oftentimes if we don't have a fixed amount of data, then that's filled with some amount of empty data, so to speak. And then the last one here is the cryptographic hash functions. This is, again, what we use in systems like Git, right? Where we're creating a one-way function that converts that plain text to a hash, and that allows us to have the digest that guarantees that the data is unique, and we can use that hash digest to verify the integrity of that message so that we know that it hasn't been changed. So there's a number of attacks that can happen with against cryptographic efforts. So one is, and there's different types. There's passive versus active, which is the first bullet here. So a passive attack, maybe we infect a machine with software, we listen for a long time so that we can learn more about a system, whereas an active attack is more about actively working to get information through a system. But there's different types of attacks. So brute force, this is where we're trying to discover that cryptographic key through a number of attempts, right? And so if we look at the bottom here, if we encrypt a cipher using a 128-bit key, right, we have a number of attempts in order to decrypt that key. At 10,000 attempts per second, it would take over 1 trillion years to exhaust the set of 128-bit keys, but just over 200,000 years with a 56-bit key. So again, this is really based on the limitations of compute power. So the stronger that compute power gets, the weaker our cryptography gets, and so it has to evolve, right, with our compute power. Related key attack, the third bullet here, is where the attacker observes a cipher. The attacker doesn't necessarily know much about it, but if we know a mathematical key relationship, then we can attempt to break that cipher. And then a side channel attack is typically where we use some other access, where we have CPU power consumption, fluctuations in electromagnetic spectrum that can give us some hints to break cryptography as well. But you think about all these different attempts, the easiest one, honestly, is the humans, right? I don't know about you, but I trust this guy, right? I'm going to put my password in right here where, I mean, he looks trustworthy, doesn't he? Right? I mean, the mask shouldn't be anything, right? He's got his COVID mask in the wrong place. That's all, right? So, right, it's always, social engineering is the one that's the weakest link, because as humans, we are typically the weakest link. So there are a number of attacks, but that's typically the one that's successful. So when we talk about software and producing software and consuming software, one of the big challenges is that software, as it's being created, as it's being consumed, can be modified or replaced by some unauthorized or some other unauthorized actor or some sort of attacker, right? And so in open source, we tend to use a lot of dependencies, a lot of libraries from a lot of different places. And it's a challenge to guarantee provenance of all of those things that we're using, right? We need to be able to trust those dependencies. We need to be able to trust the artifacts that we're using and produce software that is secure, right? But without a reliable way to confirm both the authenticity and integrity of all the libraries all the dependencies that we're using, we're vulnerable to exploits. And so this has been become a popular way to attack organizations is through their software supply chain. There's no longer can we just set up a Jenkins server and let people build software pulling dependencies from all over the place, because we can't guarantee where those dependencies are coming from, even if they're common ecosystems. So what we need is the community as a whole to adopt practices that would avoid attackers being allowed to inject exploits or vulnerabilities into our software. And of course, the risk that we talked about, data breaches, system disruptions, and financial loss is what we're trying to avoid here. So how do we do that? It's through being able to sign artifacts, right? And so this uses, of course, cryptography, because we want to make sure that the software they're outputting, which is in general terms in software development, an artifact is an output file, some sort of product, right? We're developing software, we're producing something, whatever that could be, right? Source code, binaries, libraries, documentation, all those types of things. And so we want to digitally sign those things to confirm the author's identity and ensure that it hasn't been altered by some unauthorized or some sort of attacker, right? And so we also need a way to verify those signatures in a way that allows the consumer of the software to verify the authenticity, integrity of those artifacts, checking the digital signatures. So we also have to distribute this stuff. It's not enough to just sign artifacts. We also have a way to make it easy for consumers to consume those artifacts, make sure they haven't been tampered with, and that they trust that it came from the producer that they expect it to, right? So we know that we're using digital signatures to make sure that software is secure. So we're using, for example, a private key to encrypt the hash of the data, right? This gives us the unique signature that's tied to that specific data, that artifact, whatever it might be, right? And so we use the corresponding public key to decrypt that signature and make sure that the contents of the artifact that we're consuming is has not been altered in any way, right? In software supply chains, we use the signature to verify, like I said, the integrity and the source of the software artifact, making sure that that hasn't changed or there hasn't been someone in the middle attacking our supply chain, injecting malicious code, or adding an artifact that shouldn't be there, right? The idea being that the signature ensures that the software that was received is exactly as a developer is intended. So as a producer of software or as a consumer, you should be able to guarantee that either what you're consuming is what you got from the original developer, or the thing that you're producing is not going to be changed, right? That it comes from the stated source and has not been altered. So one of the ways that we do this is through tools that have been around for a while. So the GNU Privacy Guard, this is software that is widely available that allows for users to sign bits, artifacts, right? And then verify that the software's source code has not been modified since it was packaged, right? So it provides authentication, providing that the software was created by a distributor. It provides integrity so that the software was signed using that distributor's private key, and non-repudiation, right? Assuming that the private key has not been compromised in any way, then we cannot deny the authenticity of that contributor's signature, and that gives us a guarantee, right? So software authors will sign programs using their private key, and users then verify the contents of the author's software with the public key. And so GPG is one of those systems that we can use, and one of the things that we'll work with in the lab. So get a little practice with this. So a couple of examples here, right? We can use GPG to sign things like commits and tags in Git, right? So a couple examples of some of the flags, right? So we have a tag here. We're using the -s flag to assign that tag. And we're going to use our GPG key to do that. And you can see we're listing the keys here that are associated with it. And then I can see that the tag has been written to Git, and I can also show the PGP signature that's associated with that Git commit. So this is one of the ways that we can ensure that from the developer's perspective, that our software that we produced gets committed to a Git repo, and it comes from us, and someone can validate that it came from us. And if it, when we validate using the -v switch, if that doesn't come back with a guaranteed signature, or a valid signature rather, then the consumer of that software will know that it has somehow been altered and should not trust it, right? Now, talked about how we do this in software with private keys, public keys, and keys in general. So one of the things that we have to do is make sure that we have proper key management to maintain the integrity of encrypted data, right? Private keys used in the encryption process have to be secret. They need to be generated, distributed, stored, rotated, and eventually retired, right? If a key is compromised, that's going to lead to unauthorized access. It's going to lead to a data breach. It's going to lead to loss of trust. And so you can see the diagram here from Fortanix, right? Top 5 features of key management are things like central stores, where we store our keys. The storage has to be secure. We have to deal with rotation and lifecycle management. If there's a multi-tenant environment, a multi-cloud environment, you need to deal with issues of making sure that the keys can be used in the various clouds, and then we have to make sure that we have access controls, right? So managing keys at scales, especially in cloud native, is a complex task involving typically key management systems like Fortanix offers one. Each one of the clouds offers some sort of key management system, right? So Amazon has a KMS service that is a managed service that allows us to control cryptographic keys. And typically these have integrations with different software so that instead of having private keys on some developer's laptop, that we put it in a central store, and we, in some cases, generate temporary keys for those for actors to use, so that the private key has less risk of being compromised. Google has a cloud KMS that they offer as well. Azure uses Key Vault, so they allow for managed system for keys. And then HashiCorp Vault is a open source version of this that's fairly popular. They have a nice feature called the Transients Key Engine, which is a nice way to sign things in flight so that private keys never leave the vault. One of the systems that I work with is called Fresca. We'll talk about another security framework called Salsa. This is a reference implementation of Salsa. It's called Fresca. It actually uses Vault in the the secrets engine, so that a software build system like Tecton can use the key in Vault without ever having to have access to the private key. So there are systems out there that make key management easier, is kind of the point. And each one of the clouds and even open source solutions exist that allow us to deal with keys and manage keys in a way that reduces risk and makes it easy for developers to integrate with secure ways of producing software. One of the reasons why we talk about key management and how complicated it is because there are some efforts, like I said, in the next section, we'll talk about keyless cryptography and advances there to make it even easier. But first, we're going to jump into the first lab, and we'll need to do a little bit of logistics to get everybody up and running with the first lab. But Ron, you have something? Yeah.
Hi, everyone. We're going to take a moment break because our food has arrived. So please take just a couple minutes and bring it back because we do have a pretty aggressive agenda, but please take this moment to do that. Sorry.
No, that's great. Perfect timing.
All right. It's still on.
Here, so we wanted to give you all some hands-on time here. I will be talking through, but you will have this document. Question? I believe, yes, the Google guest. Yep. So for those of you, yeah. So for those of you online, or rather on site here with me, please connect over to the Google guest if you need some Wi-Fi there. Okay, so in this first lab, we are going to be talking about cryptography in software development. So in the first lab, what we're going to be doing is two things, really. We're going to be just encrypting a file using GPG, very basic stuff. And then after we do that, we're going to actually explore the use of commits on our Git commit, or sorry, signatures on our Git commits, excuse me. So in our labs here, so just as for those of you that are not familiar with our format, the way that we have our labs formatted is we have a whole lot of really good copies. So please, by all means, go ahead and give that a read. And then next up, you are going to see that between this copy, you are going to be seeing a lot of these here code blocks. And in these code blocks, you will be greeted by a fake shell prompt followed by a command. And with that command, that's the one that we expect you to actually run in your terminal. By the way, our labs, we ran these on T3A smalls, so not very expensive. You can even, for this first lab, I wrote it myself. I actually developed it on a T3 micro, so you can go quite small with these ones, but we do have a few more labs coming up. So in this very first lab, we're going to be exploring the signing of files and also the signing of our Git commits. And those are a couple of things that Chris had talked about in his lecture. So I'm going to let you all go ahead and read a lot of the copies since we got quite a bit of time here. And so to start us off, what we like to do is actually connect out to our VMs. So for those of you who are with us on site here, we have a few sheets here for it. And for anyone that's online, you can actually do these on your own infrastructure. The way that we have these all formatted is that you can really just go from a very basic Debian or Ubuntu instance, in this case Ubuntu, and just follow the steps and you'll end up with the desired result for the lab. So once you've gone ahead and signed in, and the indicator for the sign in is going to be when your shell prompt has changed to Ubuntu at IP numbers. And that's going to indicate that you've been successfully signed in. So if you need to, though, make sure you download the key. And once you've downloaded the key, you can SSH -I to where you downloaded the key. And then after that, the sign-in will be Ubuntu, followed by the IP on the sheets and leaves on the tables there. Okay, so our very first step, we are going to be using Docker here. And since this is not a Docker class, or rather lab, what we're going to do is we're just going to go ahead and download, or rather install Docker. So you can use wget -Q capital O to https get.docker.com, or you can even just use curl. That also works out. So get.docker.com, and oops, and you put that into bash. Now I've already got it installed, so it's going to yell at me for having it installed. But after this, after a little while, and it took about a minute or so, once you've got Docker installed, pardon me, got a whole lot of, there we go. We got sudo docker version. Once you've got Docker installed, you should be able to query the version, and that's going to cover the Docker install right there. So a little bit of a background step for you there. Again, it's going to take about a minute on these T3A smalls. All right, we'll give folks about a minute or so to resolve that. And then as we wait for Docker to install, what we're going to start off with is we're going to actually install Golang. And this is where opening this in the HTML really comes in handy, because what we're going to do is sometimes we'll have some commands here, going to be a little bit complicated. So if you've got it open in a browser, then it's just a matter of grabbing the command from your browser. All right. You grab the command from the browser, Command C, and then Command V into the terminal there. And that's going to go ahead and download that. Questions? Accessing the instructions. Yeah. So if you go to yeah, we'll go to gedsf.org, go to training. And if you scroll all the way down, there's it's a very small link down here, but the training material link, single HTML, or if you preferred Markdown, then you can open it in Markdown. Question? Yeah, I'll give that a try here. You'll have to pardon me that, there we go. I'm a Windows person, so I'm a little bit, my MacBook is a little bit rusty here. And I'll go ahead and try to do that here on my terminal. All right, great. So hopefully everyone's
Do you
got
want
that.
to share your
We're going to
screen?
go ahead and download Golang version 1.23.2 directly from Google. Thank you, Google, for hosting us today. And so we are not installing it via the package manager. We're just installing it from the tarball. So obviously we're going to have to do the, or rather we'll have to extract it via the tarball. So we'll sudo tar -c to user local. All right, and then we'll xzf to go 1.23 to the tar gz. Enter that, and that's going to extract Golang over there. All right. Once that is done, we want to add the new profile or the new the bin to our path there. And that's going to go ahead and make it so that we can quite easily access the Go binary. So once this process is done, you should be able to just type in Go version, like what I've got down there, and it should return a positive result stating the Go version 1.232, just as we downloaded. And this should be valid as long as Go.1232's tarball is still up online.
Do you want to be sharing your screen?
All right, so with that, that's going to be the prep for our for the lab there. There's a few more steps we'll do, but for now, let's forge ahead. We're going to go ahead and create a brand new, we'll go ahead and create a brand new directory here, cd to lab1. All right, so we're now going to just prepare a quick Golang mod file. So, oh yeah, sure. Are folks all connected, by the way? You're all connected? The username is Ubuntu. Yeah. Yeah. All right, so I've got Chris going around the room. He'll be helping you out. All right, so with that, hopefully everyone is all connected and has Docker installed. Okay. So for the sake of keeping us going, let's go ahead and keep on keeping on. So we're going to create our first Go module here and our only Go module for this particular lab. So we'll go do a Go mod init on main, and that's going to create our new Go mod, just as stated there. And our main is going to have a simple web server to it. Yeah, question. Yeah, so for this particular step, we're just creating, this particular mod is just for this step here. And then we're actually going to create a separate, a separate repository later in the lab. Yeah. All right, so with that being said, once we've initialized our first Go module, and again, this Go module is going to be for this step, and we'll also commit it in a bit. But for this Go module, it's just going to be a simple Golang based server, and it's just going to be a hello world server that responds to port 8080 calls. So we'll go ahead and grab the code and put it into a file called main.go. Again, you don't have to type all this out. Please open it in the HTML, and that's going to, and just copy it directly into your code here. Let's see, got a couple of raised hands. Private key on the machine. So let's see, am I sharing? Oh, sorry about that. Turns out I wasn't sharing. There we go. Sorry about that, folks. All right, so is that share? Yeah, screen share. Okay, cool. All right, so is my share all active? Perfect. All right, so for the folks that are, so for the folks that are getting that would like to take the private key, let's see here. Yeah, so for the folks who wanted to go ahead and do this online, I think we have an arrangement for that. Let's see here. I'll have to ask around. I'll ask about for that arrangement there. But for now, for those of you online, yeah. So for those of you online, just please ride along with us here online, and we'll see to perhaps getting you some an arrangement on doing these here. Okay, so for the folks that I wasn't sharing for, I apologize for that. A few things that we did were we installed Docker, and then we installed Golang, and then after that we actually ended up preparing a new Go module in a folder called Lab1, and then from there we created our web server. So just a simple web server. It'll say hello world when you press or rather send a request to go. Let's see. So when you send a request over to port 8080 on this Go server, it's going to respond, and that's precisely what we're going to test out real quick. So we'll do go run main.go, and we'll run that in the background. You will have to wait about 30 or so seconds. So for the copy and paste. Oh yeah, so for that, if you wanted to go, the place to go for that would be GEDSF. So if you go to home here, and you go over to, go to the training, and then you go all the way down, and it's a link way at the bottom here, single HTML. And that's the page. Correct, yes. So just copy and paste it over, and then, oops. That is correct, yes. That's correct. Yes. Oh, no. Yeah, it's I'm just doing Command C, Command V here. Yeah. So I was just answering a question there with regards to that there. All right, and thank you, Carl, for linking the chat there. All right, so with that being said, let's go ahead and we've got our code going, and so what I should be able to do is curl localhost at port 8080, and we should see that I received the hello world for this particular exercise. So this is the code. Now let's go ahead and actually encrypt it, because right now it's all in plain text. A simple cat on the main.go is going to show us, well, all of the code. So let's go ahead and do a little bit of protection on this. And to protect this, we're actually going to be using the GNU Privacy Guard, or GPG utility. In these VMs, the GPG utility is already installed. So if you do GPG -- version, just as stated on the lab, you'll see here that you should have something like version 2.4.4. If you're following along on your own infrastructure, you might have to install it. And if you wanted to install it, then at least on Debian and Ubuntu, then it's going to be on sudo apt update there, and then GNU PG. So with that being said, let's go ahead and first start off with generating our key. So we'll go GPG -- gen key, and we'll just enter a name. For here, I'll just enter GESF 2024 attendee. And for the email, I'll just go with what's printed here with attendee at GESF 2024. All right, you go ahead and confirm that. It's going to ask for a passphrase. I'll use something super secure right there. All right, and it's going to ask you to peck around the keyboard, and that should generate your keys. So from there, once you've generated your keys, you can go ahead and do a GPG list keys. And that's going to state that we now have a key that's available. We have a public key, which we can potentially use for signing. And then there's another key here for encryption. And the second key is the one that's going to be in play in the next step. So this is Global Encryption Day. And what's a Global Encryption Day without some kind of, well, encryption? Are there any questions at this point? Yeah, sure. Yeah, so right now, all I've done is I've just generated the new GPG key. I haven't done any kind of commit message or anything like that. I've just prepared the keys that I'm actually going to use to verify my identity. So that's all I've done so far. We are going to be using this key later, though, when we sign the commit message. But for now, we're actually going to use this key to encrypt the code that we've just created. Yep. All right, so let's keep on going there. So let's confirm that everything has been created. We do have a Go mod and a main.go. And for now, let's go ahead and just, well, encrypt it. So what I'll do is I'll GPG and I'll create a file called main.enc, encrypted, and I'll go encrypt. Let's see here. We'll do that. All right. I'm going to go ahead and encrypt that. It's a little bit cut off there. Sorry about that. Come on. Come on. There we go. There we go. All right. So we're going to encrypt just like that. All right. And next, we want to actually state who's going to get it. So the intended person that's going to get it. So I'm going to use the same email that I created the key for. That way, this person is actually going to be able to, with my public key, actually decrypt it. So we'll go ahead and we'll encrypt. We'll do -- encrypt over here. All right. Oh, and then of course I need a main.go. All right, so main.encrypted exists, and now I should now have a main.encrypted file. And so comparing the two, if we cat main.encrypted, we're going to see that, well, it's a whole lot of encrypted text. So at this point, I've now encrypted and obscured the contents of my file using the GPG key. Yeah. So now the only person that would be able to decrypt this and see this in plain text would be the stated recipient, which is going to be based on this email right here. And I'm going to show you how that's going to be done in the next step. All right, so, oops. Okay, so next I'm going to go ahead and decrypt it. So basically now I'm going to say, okay, I would like to decrypt the file. And in this case, this particular file is going to look for a specific key, which I should have passed over to the person that I intended to decrypt this. Now, I'm going to be skipping the step of passing it over because I'm the one I already have the key loaded here. And that was the one that I generated a little bit earlier. List keys. That's the one, that's this one right here. So I'll do GPG and I'll do output of main.dec. And then we'll do a decrypt and followed by main.encrypted right there. So what this is going to do is it's going to take main.encrypted, find the key that has the recipient's email on it, and then it's going to decrypt it, and that's going to output to a file called main.dec. It's going to ask me for my password. So, all right, there we go. And now I should have a main.dec file that is now in plain text. So this is actually a very old method of encryption. This is something that folks were doing for things like their emails way before I was born. So definitely, this is one of the ancient techniques, so to speak. Correct. So the question, yeah. So the question here is GPG an open source tool and mostly encrypt? Yeah, sorry. Included with most Linux distributions? Yes, it is. So it's pretty, again, it's a pretty an old technology, but a lot of people still use it. And as we're going to see when we get to the Git commit encryptions, or rather signing, we actually end up signing the commits with that same key. Yes. That's correct. Yes, you're going to give a public key that's intended for distribution, and then you generate the signing keys, the ones that you do the signing or encryption with a secret key. So you distribute your public key, and then you actually keep your secret key, well, as secret as possible. Correct. Yes. All right. So we've got our code. It's been decrypted. Now let's go ahead and take a look with some signatures then. So another thing that you can do aside from encrypting your files is to ensure that if someone needs to, they can verify that you were the one that actually produced that file. So we're going to go ahead and I'm going to reduce the amount of typing that I'm going to do in the interest of time here. And so what we'll do is we're going to create a new signature and we're going to detach it, and we're actually going to apply it to main.go. So what I'll do is I'll just follow the instruction there. We're going to create a new file, a separate signature, a detached signature that is going to be attached to main.go. And so when I want to verify this, I can actually use this signature file to perform that verification. So I should now have a main.sig file, and that's the one at the bottom here. All right, and then if we cat it, it's going to be a little bit obscure. So that's intended. We don't want this sort of stuff running around in plain text. So what can we do with this? Well, first off, we can verify if the signature actually applies to this particular file. So if we do a GPG verify on main.sig and then associate it with the file that we signed with the signature, we'll see here that I got it incorrect. That's what happened. Let's see right there. Yep. Thank you. Yeah, there we go. All right, verify. Thank you. All right, so there we go. Now you are able to confirm that this particular signature is good for this particular file. Now, having it detached is one thing. You can make it so that you actually embed the signature in, and that's actually one of the more common ways that you see signatures passed around. So what if we do something odd? Let's go ahead and modify the file. And before we modify it, let's just create a real copy of it. And let's go see if the signature is still good for that. We haven't done any kind of tampering with this file yet, so it should still be a good signature. The signature still matches this particular set of bits for the file. All right. Now let's go ahead and add a little bit of new content here. So let's go echo our new text like that, and then it's going to now create a modified main.file or main.go file. Let's try the signature again. We can see here that now, after we tampered with the file by adding a new line, we now get a bad signature. Now we know that somebody has actually tampered with this particular file, and thus we might not be able to trust it as well as we should be able to. Okay. Let's see here. All right, cool. That is correct. Yes, the question there was the signature is primarily for validating the integrity of this file, and that you are the one, or rather the intended author was the one that actually gave you that particular file. And it's this sort of trust that you want to have when you're dealing with encryption, because it's definitely something that could bite you much later down the line. So you want to make sure that in your workflows, automated or otherwise, there's always some sort of establishment of trust. And back then it was GPG keys. These days it's things like software bills of materials and even other kinds of manifests that will do that. So talk a little bit more on those. Correct. Yes, that's correct. Yes. That's correct, yes. So the order there was going to be to encrypt the file. Yeah.
Repeat the questions, these people aren't remote.
Yeah, I understand. Yeah, so the question was about just clarifying what the order of operations would be. So if you are encrypting your files, obviously you'll go ahead and encrypt the file. Sometimes you might not encrypt the file. It really depends on how severe it or how classified it is for you. But let's say you've produced the file and now you want to sign it. And once you've signed it with your key, and by the way, in your key, you actually have a separate encryption subkey, which is specifically just for encryption. And you also have a signing key. And that's the one, that signing key. Oh, and in addition to that, you have the public key too. So you want to make sure you sign it, and then you'll distribute your public key just like you would if you wanted someone to decrypt it. And then once you've signed it, and typically this is where you see someone posting the actual signature alongside the file. If you've ever installed something for Linux like that, you'll see that. And then after that, the intention is that if you want to find it or if you want to verify it, you have the option to do so. Yeah. So it's somewhat optional, but more and more folks, especially in today's world, are making it more required to do so, especially if you're automating things. Yeah, so the question, and I have to repeat the questions for folks online. Yeah, so the question was, is encryption required? Not necessarily. Again, it depends on how classified your particular file has to be. And then the important part is that when you distribute it, that anyone else is going to be able to actually verify that you are the one that distributed it. And again, it's a chain of trust that you want to establish. And signatures can be on files, they can be on commits, they can be on emails, they can be on a whole lot of things. As long as you're able to establish that trust, that's the really important part. All right, so let's go ahead and I'll go on. So actually, in the next one, what we're going to do is we're actually going to make a new file here. And we're actually going to do an attached signature. So previously we had a detached signature where the signature was actually a separate file. In some cases, you want to just have them together. And that's where this next command is going to be. We're going to create a new file, and we're actually going to omit the detached or detached sig operator here. And that's going to make it so that if you want to verify this particular file, then you can do gpg verify on main.go.sig. And we can see here that the signature has been embedded into the file. And if the intention was simply, let's just very quickly distribute it, but still give people the option to actually verify that it's the real file, then by all means, let's go do that. So now what I'm going to do is I'll go ahead and this particular file here, by the way, is still, it's still somewhat obscured. So what we're going to do is let's go ahead and recover this file. So I'm actually going to go ahead and remove main.go. Next, I'm actually going to decrypt the main.go, and I'm actually going to decrypt it from this particular signature or the signed file. So now, so previously, if you missed it, I removed main.go. And now what I've got here is essentially I reversed the encryption there. And now we've got it, I've gotten it back. So if I do cat main.go, we see here that I've got it back in plain text. So with that, that's going to be the first part of the lab. So thank you everyone for the patience there. And so in the last 10 minutes or so here, I'm going to go show you some signing of commits. And this is where the Docker install comes in. So in order to, yeah, go ahead, question. Yeah, sure. So one of the most common cases where you'll see attached signatures are when you sign things like, say, Git commits, for example. That's actually because a lot of the systems, especially on GitHub, One of those things is if you provide your private key on your account, which allows GitHub to verify the signature attached to your particular commit, then it will show the little verified badge on there. So that's actually GitHub doing that based off of the attached signature. Now, in terms of the detached signature, in terms of a public example, I can't really think of one right now, but my usual fallback is that falls to policy in terms of what's the internal policy here. Are you going to be allowing attached signatures, or are you not going to be allowing that? And that every signature must be stored in a separate, say, metadata store where multiple systems could potentially get them to. Yeah. All right, so speaking of multiple systems, let's go set up yet another system here. Again, I'm going to be minimizing my typing here by just copying and pasting. So I'm going to create a new, we're actually going to self-host a Git repo here. And so what we're going to do is we're going to use the Git daemon. And that's basically going to allow us to have a local Git server, which will host a repo for us that we can push and clone to. This was primarily done so you didn't have to sign up for GitHub accounts today. So in this particular one, we are actually just going to invoke the Git daemon using using just the Git daemon script. We're going to have it reuse the addresses. Its base path will be whatever path we give it. We're actually going to run this in a container, by the way. We're going to export all of the repos that are being served by this repo, or rather this daemon. It's going to be in verbose for logging. And then finally, enable receive pack will allow this Git daemon to accept pushes. So if you ever were wondering, hey, can I get a local Git daemon or a local Git server, the Git daemon is the way to go. We're doing it in a container though, so that's just going to give us a little bit more leeway and an opportunity to do more of these. So it's a script. I'm going to want to make it an executable script. So I'll change mode it to +X. That's going to make it executable. And then I'm going to pack it into a Docker file. That's just going to use Alpine, which will have the Git daemon inside of it. And then after that, we're going to initialize the Git daemon using the script. And it's going to be, the working directory will be /git, which we're actually going to attach to a file, a host path. All right. And then I'm going to just pop this in the Docker file again. It'll be based on Alpine Linux. It will add the Git daemon. It will copy the script in. It will serve on /git, at least internally. And then we're going to just run the Git daemon shell script. That's going to get the Git daemon up and running. All right. So the next thing is we need to build it. So again, what we're going to do is we're just going to do a Docker build, give it a little, give these little T3A smalls a little bit of an exercise here. And now we have a Git daemon container image. And now what we're going to do is we're actually going to run a local Git daemon container. The /git directory in the Git daemon container will be attached to our host at /temp/git. So we'll go ahead and do that. All right, so if I do sudo docker ps, all right, so what we'll go ahead and do is we'll get our Git daemon all up and running. It's going to be served on the very first one, and that should be 172.172.17.02. That's the first IP for every Docker container if you've got nothing else running. I'm going to make my life a little easier. I'm going to reference it by an environment variable. So we'll just do that. And let's just make sure Git daemon is active like so. If it says ready to rumble, you're good to go. All right, so now we need to create a repo that's going to serve from. We're just going to create a bare repo, and it's going to be shared by everybody, and it's going to have the branch of main. It'll be stored locally on our host at /temp git hello world, which is the /git directory in the container. We do have to use it as sudo because the Git daemon is running as root. Yes. Oh, let's see. I believe I adjusted that. Should have it there. Yep. Questions? Yeah, I think for questions, that's for. Oh, interesting. Okay. Yeah, sure. Let's go ahead and stop it real quick, and then we'll reestablish. There we go. Okay, great. Sorry about that, folks. All right, so we're going to initialize our Git repo, and that's going to exist at the within the Git daemon, and it's going to be served by the Git daemon. Now, we're going to leave it alone. We'll let the Git daemon do all the management of this repo for now, and we'll just go back to the lab1 directory. And now we should be able to clone the hello world.git that we just initialized. It's going to be an empty repository. And if we go over to hello world, we'll see here that we've got that going. All right, so it's an empty repo. So let's get to signing commits. That's the main event here. So what we'll do is let's go ahead and configure an email for this particular Git session here. So we'll just do a git config. And next, I'm also going to create a name as well. These are going to be attached to my commits. Once that's done, I'm going to go ahead and copy over the main.go over here. We've got it. So let's just do a standard commit, git add, and then git commit. We'll do -m, first commit. So this is just a standard commit. There's no kinds of signs. Git log -1. Okay, so no signs at all. So the only, as we point out in the lab text, the only way that we can figure out who did this commit was just based off the name and email that we provided. And there's no secondary mechanism for that. So I'll go ahead and push that over. And that is going to be the very basic. So again, as long as we trust the person who has control over this Git repo and has that email and the email and name associated with them, then we might be able to trust them, but I don't have any other way of verifying that. So what we'll do is let's make it so that we can actually sign our commits, and we're going to do that with our secret keys here. So we'll do we'll do GPG, and then we'll do list secret keys, and then we'll do the key ID format of long. All right. So what we want to do is we want to actually grab one of these keys, the sub keys technically, and what we want is we want to make it so that this particular Git client is going to use that key for signing commits. So I'm selecting this sub key right here. Yours might be different on your machines. And so what we'll do is we're going to do a git config, and then we're going to set the property of user.signingKey. And this is going to be where we can then state which key we want. That's this one right here. You can tell that it's a signing key by the little bits right here. If it says S at any point, that is a signing key. If it says E, that's an encryption key. So this one is going to be specifically used for just signing. So this is the one that we want to feed into our Git. And so at this point, let's go ahead and just add another file. So supposedly, I should be able to create a new file like hello world to my README. I'll go ahead and add the README, and then we'll get status. We've got that. It's all there. So now what can we do? Well, first off, there's one thing that we have to do, and that's to let the GPG agent actually ask for a password. There's a little note here that states what kind of an error you would get, but make sure you, at least in this lab, make sure you export this GPG TTY equals the current TTY. And now, if I do git commit -s followed by my message, and I'll just do add README, watch what happens. Well, I should have been, well, since I entered my password just a few minutes ago, it actually just skipped that part. But if we do a git log -1, and then I do show signatures, oops, show signature, excuse me, like that, we can see here that now, not only do I have my name and email on it, but now if you have my key, you'll be able to actually use that to verify that I'm the one that did that particular commit. So it's all about that secondary mechanism to ensure that this commit came from a trusted source. That's correct, yes. Yeah, so the question was, that's what I'm showing, the signature being attached to this particular commit. All right, and let's just go ahead and git push too, why not? So because when I do the push, because the signature is attached to the Git commit, anybody who actually goes into this Git repo and clones it and has my key, they can verify that I'm the one that did these particular commits. And yeah. So in this case, if you wanted to, what they can do is they might end up just doing something like a GPG verify on it. But in the case of something like GitHub, it has that little verified badge that will do that for that, as long as the person who made that commit uploaded their GPG key, their public key, onto their account there. So it would already be done. And the thing is, especially in a lot of open source projects, they will require that you have that enabled, that your commits be signed. And that's something you'll see very, very often. All right, so yeah, so in this case right here, the best way I can verify is actually with a git verify commit. So verify commit here. And if I grab this commit hash, oops, sorry, verify signature. There we go. Verify signature. I believe it was that. Sorry about that. There is a command that you can actually verify with that. It's further down in the document there. Yeah. All right. So that being said, though, if you wanted to show the signatures, it is just going to be in that Git, and you can do a show signature. You can do there's a verify command. Again, it's further down here. So let's go ahead and actually make a new clone of it. So we'll do just the CD, and we're going to make another copy. So just, yes, that's it. Git verify commit. It wasn't a minus. There we go. So git verify commit, and it'll give you somewhat of the same. Oops. Have to be in the, there we go. Yep, so that's going to be the way that you can do that. And this is predicated on the fact that I have the public key here. Correct, yes. And then we have the key that it was signed with as well, which hopefully you have the public key version of it. And that's going to be the thing that gets verifying for the signature. Correct. I'd have to distribute the public key, yes. Yeah, so I was just getting clarification on the reason why I didn't have to, download keys is because I already had it in my local key ring get keys.
How does it work in a project where there are multiple developers and they each will have their own public key against their any key? Who will manage that for all of them to make sure the verification can happen? But you see what I mean?
Yeah. So
If you want to adopt.
Yeah, so the best one that I can give you actually is with Arch Linux, because with Arch Linux, what they do is they have a lot of developers, and in order to verify all the packages, for example, I actually end up having to download a whole package of essentially a key ring that just downloads every developer's package, and I actually have to update that pretty often. So you might end up having to create a package that actually just has all those keys, and that you would have people go ahead and download on the regular to maintain it. Yeah. All right. So with that, then that's going to be that. Let's go back here. We're just going to verify that let's see here. Okay. So it looks like I didn't get that yet. So what I can do is, since I pushed it over, or the commits over, if I head on over to HW copy here, and if I do a git log -1, and then I'll do show signature, we see here that the signatures are on this new copy of it, because all the signatures are still attached to that. And if I wanted to further verify it, then I'd have to acquire that public key in some manner. Again, it could be some package or some other thing like that, which would load it on my local machine and I'd be able to verify it myself. Yeah. All right, so with that, if you wanted all your commits to be signed, there is a property called commit GPG sign equals true. This is going to effectively add -s to all your git commit. And that is going to make it so that you don't have, it'll just ask you for a password if you have one. Yeah. Yeah, sure. Q&A, got one. All right, so to Chijan's question here, after we encrypt the source files, will it still be able to compile and run? If we want to avoid others to view why don't we just provide the compiled binary? Yeah, so in that case, yeah, absolutely. So when you encrypt the source files, they do become this encrypted, it's just a bunch of nonsense characters, basically. So you are correct. If you don't want people to view the source code, then you can simply compile the binary. The point of the encryption is that if somebody breaks in somehow, and you don't want them to look at that source code, even if they broke in, then what you would want to do is basically encrypt at rest. So when it's not in transport, when you're not sending it around, you want to make sure that that particular file is going to be as protected as possible, because you never know, what if someone gets into the repo? What if somebody gets into our file? What if somebody gets to our server? So to Chi's question, hopefully that addressed that. All right, so I'll mark that as addressed live. Thanks, Ron. Okay, so yeah. So in that case, just based off of my personal experience, I haven't gotten that far in that particular rabbit hole. I do know that there might be some policies out there. Yes. So it would probably be something for the super classified files in those enterprise types or government types for sure. But if you're doing open source, and obviously you want as many collaborators as possible, and really the thing that you have to verify is, is this collaborator a legitimate collaborator? Yeah. So it's more, you're going to encrypt the files that are really important to you, and everything else is going to be, open. So yeah. All right, so there's one last thing that we want to do here, and in the interest of getting us onto the next lecture here, basically, I'm just going to summarize what we ended up doing in this particular section here. So far we have one signing key, we have one encryption key, and that particular signing key is pretty powerful. It's actually the secret key. So that's the one that can not only sign files and commits, but it can also generate them. And in some cases, you don't want to keep that around, especially if you don't want someone spoofing it and generating signing keys and then ultimately gaining control, or at least gaining the trust that you already might have. So in the last section, what we end up doing is actually we end up splitting off, or rather removing, the secret key. And then we'll actually just import or first off, we create a specific signing key. So it'll only sign, it can't generate anything. So we're actually going to edit the key. So we do GPG edit key. All right. And then of course I need to provide my key there, which I don't recall. So sorry about that. We'll do a GPG list keys here, and a GPG edit keys, edit key. And then we'll grab this particular public key right here. All right. So now what I'm going to do is I'm going to add a very restricted key. So I'm going to put in add key, and all I want is a signing key. So I'm going to do an ECC signing key, and we'll do 25519. This is going to generate the same kind of signing key as the previous, and we'll just do 2 years. Type in yes, and I'll be prompted for my password. There we go. All right. So at this point, now I have a very specific signing key. Okay. So I have a very specific signing key. And at this point, now I can go ahead and save that. Now I have a signing key, I have a secret key that can generate, and I have an encryption key. So once that's, yeah, go ahead. So the secret key, that's the one that can not only sign, but also generate keys. And that's not something you want to have lying around. Because if someone gains your secret key, they can generate fake signing keys, and they can co-opt your trust, whatever you might have on your particular key. All right, so what I'll do is what we end up doing is we actually set the new signing key as the one for our Git. All right, so that's this one right here. Just that one right there. And now anytime I sign, it's going to use that new key or that new sub key. And so if I add a new, if I go ahead and add a new file here, oops. So I'll go add our new file and we'll just commit that. Git add, git commit -m, new git ignore. All right, and then there we go. So this time I had to be asked for my signing password. And so with that, what you're going to see is that the sub key itself is not actually going to be visible. So if you do a git log -1 and then show signature, you'll see there that you don't really see which signing key was used for it. You can only see that this particular key overall was the one that was used. Okay, so what we ended up doing then is we actually ended up saving our signing key, or rather we saved the secret key, we saved the secret key, we saved the public key, and we saved the sub keys, which includes the encryption and signing. So we'll go ahead and save those. And let's see right here, we need to grab that particular key right here. All right, so I'm going to do that. This is me getting the public key only. And then next is going to be the signing the secret key. All right, so 1, 2, 3, 4. And then lastly, I'm going to do the secret sub keys. Yeah, sub keys. Yep. All right, so we do sub keys. All right. And then after that, I'm actually going to remove the secret keys actually by just deleting them, and I'm going to re-import only the sub keys. So then that way, I only have the ability to sign and encrypt. I don't have the ability to create anymore. And that's going to be the rest of the exercise there. So we see here that we went ahead and deleted this particular key. Yes, it's going to ask me several times to delete all of the keys inside of that. And now what I'm going to do is I'm just going to import the signing keys myself, or rather the sub keys. And now I'm free to actually sign. And that's going to make it so that now I don't have my secret key around for someone to just generate whatever they want from my secret key. So with that, at the very end, we're going to assign another file, and we see that it all still works out. The only thing that we can't do is actually create a new signing key. You're going to see that if you try add key again, it's going to state you need the secret key, which we can re-import, and we actually end up doing so in the end here. So with that, that's going to conclude that very first lab. So we took a look at encrypting files, which is something you may want to do for the super sensitive stuff. And then we also took a look at signing files, which is going to allow folks who need to actually verify that that particular file or commit whichever artifact is going to be the one that you want. And then at the end, we signed some commits, and we took a look at how you would help sign those, help handle those signature keys. Yeah. The question was using one key for signing encryption. It's typically bad practice because you want to make sure that you want to have explicit control over the capability of encryption and signing. And typically what you end up doing is you put these keys or the key files into something like a YubiKey or some other kind of hardware, even a USB inside of a lockbox, that should be fine. Could be better, but it could be some, as long as it's not on your computer and as long as you can actually retrieve it, then you should be good. So actually, there are different. Yeah, sure. So the question was about the whether there are different, or what are the best practices around picking an encryption key and a signing key algorithm. And typically that's something that you kind of have to keep up on in terms of what is the most secure algorithm at this time. We used to have like RSA 2046, and then now people want 4096. There's a lot of it's something that you have to kind of keep up on that. And that the best advice I can say is when you are adopting a signing mechanism or when you're generating a new key, go for the one that is typically either the newest one or the one that, if you've done a little research, the one that is probably in use by various governments or other types of big businesses like that.
Because I saw when it was signed only, it said ECC for encryption, it said RSA and other stuff. So I was wondering if probably can use for signing versus encryption.
That's correct. So the question was about, are there different algorithms used for signing and encryption? Yes, typically.
10 and 12 over there, ECC, sign only, ECC, encrypt only.
Yep. All right. So that's going to be it for me for now. Thank you everyone for the patience on that. Yeah, thanks so much. And you'll be seeing me again. All right, Chris, I hand this over to you.
Is this
Hello.
Yeah. I think I put it in wrong.
I think that's, yeah, that works. Thank you. Sorry, runs our cup in our. I know how many engineers does it take to screw in a microphone. Okay. So one of the last things that Christian did there was exporting the keys, right? He was talking about removing the private key from GPG, and then he was talking about taking it offline, right? So we talked a little bit about key management systems in the last few slides of the first section, right? We have to make sure that we protect the keys that we're using to sign artifacts, because they can be compromised, and then someone can create more keys and then sign more stuff, and then they're basically signing things as you, and it's not you, right? And so they can inject malicious payloads where they shouldn't be. So we're going to talk about some improvements to the ecosystem, because key management is complex, right? If you do it wrong, then you risk a lot. So there are ways to have keyless cryptography. We put these in air quotes because it's not exactly keyless, but there are ways to use identity with keys in order to sign artifacts in a way that we don't have to manage keys long term. So there's a a project known as SigStore. This is a sub-project of the Linux Foundation, part of the Open Source Security Foundation. They've got two sub-projects, SigStore being one of them. The idea behind SigStore as a project is to improve security overall in the open source software ecosystem and to make things easy. You cannot underestimate easy, because when things are hard, we don't do them. Think about things in your life that are difficult to deal with. You probably avoid them or leave them for last. You're procrastinating about those things. So one of the I would say one of the beautiful things about Docker as a software, if you're familiar with Docker, and in general, their old CTO, Solomon Hykes, I always like to repeat what he said, which is the tools should get out of the way, right? Developers should be free to do their work and not have to worry about configuring a whole bunch of stuff, configuring all the tooling to get their work done, right? Smart words by a smart guy. If we make the ecosystem, if we make things easier on developers to sign artifacts, then we're more likely to do these things, right? And we need adoption from the entire ecosystem in order for this to work. So SigStore aims to make the security of open source software easier on developers and provides for free tooling and automated issuance of keys and tracking of artifact signing through transparency logs. So we're going to talk about the project and how to use it so that you can benefit from the project overall. The idea being that we use a number of different services in the SigStore project. The first one on the top here being Fulcio. This is the certificate authority. What this will do is issue short-lived signing certificates. This way we do not have to maintain long-lived keys, right? We just talked about having to export the private key, getting it offline, right? Using SigStore, we don't have to worry about this anymore because we can have Fulcio issue short-lived signing certificates. And when I say short-lived, I'm talking about minutes, because what you're going to do is ask for the signing certificate or signing keys, sign the artifact, and then throw those keys away and never use them again. And that allows us to not worry about management of keys, but have trust built into the system, right? And so every time one of these keys is issued, there's a transparency log that shows the timestamp of when those things were issued, so that someone can go back in time and say, okay, I know that this artifact was signed at, noon Pacific time, right? But if I go back and look at the log, the key was issued at 12:15. Well, that's impossible. How could I sign an artifact at noon when the key was issued at 12:15, right? You know you've been duped at that point because there's no way that key existed, right? So we have this transparency log. It's about building transparency in the community when we have when we go to sign artifacts. Recore is the second project here. This is where we record the artifact signatures with timestamps, right? We have issuance, and then we have the artifact signatures also in a transparency log, right? So we record the artifact, the signature, and the timestamp all together. We can verify that the artifact was signed within the window that the certificate was valid. And this provides full transparency for those activities as well, right? There's a couple different tools that we'd use on the client side, which are cosign and getsign, specifically designated for signing container images. So if we're using Docker or Podman or any of the other container tools, and getsign provides a secure method to sign work with the transparency logs of Fulcio and Recore automatically built into the ecosystem, right? This way, I don't have to worry about managing keys. And you think, well, how do I verify my identity, right? In this ecosystem, if I don't have a key, if I didn't generate the key, somebody else generated the key. Well, think about how you log into your laptop, how you access systems in your organization or in a school. Don't you already have an identity? Maybe it's an OpenID Connect identity or some other type of identity provider, right? Why am I managing two identities when I could just manage one, right? And usually your identity tied to your school or your organization includes a biometric or some other type of YubiKey or two-factor authentication, right? We're already validating that we are who we say we are with non-repudiation. So why would I have another key that I have to manage in some other system that's complicated when I could just use who I am, what I am, to say, okay, this is me, give me a key, I'll sign an artifact, and then I'll throw that away because it's not going to be valid after 10 minutes. And I know it came from me because these systems hook into OpenID Connect. They hook into my identity provider, right? We use these systems every day, right? You log into your Gmail, you log into, I don't know about you guys, but I have 1 million authenticator codes that I've scanned on my phone, right? For every account that I have, right? So we use that as a way to say, this is who I am. And now I've signed my artifact and I don't have to worry about managing keys. Yeah, question. So the question was, where's the biometric stored? Well, so SigStore itself is not storing this stuff. What it's doing is integrating with existing identity providers. So if you're using a biometric on a phone, right, it's through the phone, right? So it's with the identity provider you're already integrated with. If you're using a YubiKey, it's plugged into your laptop, right? Whatever security systems you're already using, it's integrating with that. And so that way, that's already established. All we're doing is integrating from the SigStore side to existing systems, right? Why reinvent the wheel, right? We already use all this stuff every day, right? So how does this work, right? Step one, certificate requests, right? Some client, like cosign or getSign, will request a certificate from Fulcio, right? We have to provide a verifiable OpenID Connect identity token, right? Some sort of identity provider has to be involved. And again, we log into these systems every day. So if you have some type of identity provider, like Google works as an OpenID Connect, right? Thank you, Google, for letting us use our space. Thank you, Google, for providing OpenID Connect, right? So we get that token from that provider. It has the user-specific details. And typically, again, you have to provide a 2FA, right, to get to your Google account or whatever account it is. Provides a biometric or some sort of authentication token, right, from one of your apps, right? So now we've validated that we are who we say we are, right? Step two, we get the issuance, right? Fulcio will verify the provided identity token because we have that integration, and then it issues that short-lived certificate that's tied to that identity, right? We're not managing a key that has nothing to do with who we are really, right? We're managing a key that is tied exactly to us, right? We don't have to manage private keys. SigStore services never get that private key, right? You get it to sign your artifacts, and that's it. Step three, you go to sign it, right? You use the client tool to sign the artifact using that certificate, right? The digest, the signature, and the certificate are then stored in Recore. This is the transparency log so that someone can come after the fact and validate what you did, right? Without having to, you don't have to distribute your public key because we can get that from distribution mechanisms through Recore and validate it that way, right? And then we have public auditing of signing events through timestamps. So anybody can search. We'll show an example of searching that for later verification. Step four, artifact validation, right? If we want a verification, rather, we want to verify an artifact, the SigStore client will verify that signature on the artifact. using the public key from the certificate. And that's the distribution of that is built into the system. That ensures the identity, that the certificate matches the expected identity that was associated with the original OpenID Connect user. And then we check the certificate signature against the SigStore's root of trust, which comes from Fulcio, but for proof of inclusion in Recore, right? The idea is this is supposed to be made easy on all of us to make signing artifacts less complicated, right? We spent a whole bunch of time managing a whole bunch of keys, right? But we want to use the systems we're already using, right? So this is just kind of the flow, how it works, right? So as a developer, we request a certificate. This is kind of what the steps went through, right? We authenticate that with an OpenID, right? Fulcio then will provide the signing certificate. It'll publish that signing certificate in the Recore transparency log, right? We can check signatures in the log. End users can do that. And we have a signed artifact that is distributed, and end users can find that artifact, download that artifact. Developers can publish that signed artifact. And we have full transparency from the developer all the way to the end user, right? And this doesn't have to be developer to end user. This is just kind of the flow they talk about with SigStore. This can be artifacts upstream where the consumer, the end user, is another developer using some smaller piece of the ecosystem, right? So it doesn't have to be a container image, right? Cosign is container images, but get sign is just code. Yeah. No, so in the transparency log, the record of that is stored, and you see here that we have public auditing of the timestamps, and then we have the certificate is stored in Recore, and they can get the public key from the certificate that's issued. Yeah, so the question was, we're getting the certificate, but we're getting the timestamp from the from Recore. Yeah, we're getting all that information from Recore, and then we can validate the certificate. We can validate the signature from what we get from the log. Yep. So 2 tools, as I mentioned, right? Cosign is number 1, right? So we call this keyless, right? There are keys, right? As I mentioned, we generate with Cosign, we generate the key pairs. We sign a container, we store that signature in the registry, and we can verify a container against the public key. Now, it depends on the ecosystem. With container registries, the OCI specification has expanded. So the OCI is the Open Container Initiative. This is a standard by which all container images are written. Think of it as a format. So the format of the actual artifact you produce is a tarball, right? Container image could be an Nginx web server, an SQL server, your Node.js app, whatever it might be, right? But that's just the code contained in a distributable artifact. But what you also need is the software bill of materials. You need the signature files. You need attestations. We'll talk about all of these things. The specification for the API that the OCI uses allows us to store all of those things in the container registry and retrieve them all from the container registry. The idea being that it's one single place where we store all of the information about a piece of software, whatever that is, right? Whether it's an Nginx web server or a Node.js app, whatever it might be, right? Your Python app, that kind of thing. That way we don't go, well, I got to download the tarball from the container registry, but then I need to get the metadata about it from some other place, right? I'm not making all these calls, all these API calls to these different stores. I'm doing it from one place. So for Cosign, we can actually take everything we need to provide provenance for that artifact from one place. And that's provided by the OCI, the Open Container Initiative registry specification. So Cosign integrates with that API, right? And so we store the signatures alongside the images themselves, and then Recore just gives us the transparency log for the timestamping, right? So if I want to verify that, in my previous scenario, I was talking about making sure that, you know, the artifact was signed within the time window, that sort of thing. I can do auditing through Recore in that case, right? And so again, we make the signatures created by the short-lived certificates from Folcio, and this mitigates the risks associated with long-lived keys, getting rid of that as an attack vector, right? Now, all these projects exist in the public, so that, and they're free to use, but organizations in general can also run private instances of the transaction log. So let's say I don't want to have all of my, I don't want to have all of my information all out there for everyone to see, but I want to share it with my own internal organization. I can run a private instance of the transaction log, and then all of the users within my own organization can validate all of the metadata and all the signatures internally and not worry about leaking that to the outside. So there's really two ways to do it. But all the free stuff, all the community verifiable transaction log is all run by the SigStore project, right? So this is an example of using cosign to sign and verify images. Yeah, okay. So a couple things to note, there's some caveats. We cannot sign images where we don't have write permissions to registries. So, right, we have to integrate with that Open Container Initiative registry, whatever that is, whether it's an organizational one, if it's a public one, if we have an account. A lot of the registries out there will allow you to make a free account, right? You can make one on Docker Hub for free. And then you have write permissions to your own account. But we have to also publish the image to the registry. So typically what happens when we create a Docker image is the container runtime, whether it's Docker or again, Podman or whatever tool we decide to use, we build the artifact, in this case, the container image, locally. And that's cached on the disk of the system that built it, right? Well, that's not very useful. It's not distributable anywhere because it's one laptop, one host, whatever it might be, right? What we do is we push that to the remote registry. That's called publishing, right? Cosign only will sign images that are being distributed. It's not going to sign something that's local because there's no reason for someone else to validate some local image that I'm just going to use on my laptop, right? This is about distribution, right? So another thing to note is that it will also complain if we try to sign container images by tag. So there are pointers, just like in Git, right? I can tag a commit hash in Git. I can tag a container image. A tag is just a semantic pointer to a hash. The problem with semantic pointers is that they can drift, right? I can make that Git tag point at another commit hash. I can make that container image tag point at a different container image that was rebuilt 5 minutes later. It's still the same tag. So it's the semantics that make it vulnerable. So cosign knows this and knows that we should sign the image digest or the SHA hash. And you can see here in orange, whoops, the SHA hash that we need to use for our signing. We can't use the tag. However, oftentimes on the validation side, consumers don't know what the SHA hash might be. And oftentimes we pull an image from its tag, right, from a remote registry. So to make it less complex on the consumer side, we can verify using the tag. So that's okay. But we have to sign using the digest because that's the thing that guarantees zero drift, right? If anything changes in that image, that SHA hash will be different. So that's what we sign, right? So here we look at the digest. We can see that in orange. We generate our key pair, right? We then use the sign command using our cosign key, and we sign the hash. This is the first part of this in green is the host name of the registry that we pushed it to. The second part here before the @ symbol is the repository name. And the last part is the hash, the image bits that we're signing, right? Asks us to enter a password for the private key that we set when we generated it. And then we also show the verification using the tag. So in this case, we sign with the hash. And here, this is 3.0.0 is the semantic tag that points at the hash. And we use that to verify, and it will validate the claims, that the image is signed correctly and has not changed in any way since we initially signed it, right? So just kind of a lightweight example of going through here. Okay, so the transparency logs, right? The idea behind the transparency logs, it's this immutable append-only data structure, right? We can't have any mutations in the transparency log because then, of course, we would have issues where we couldn't trust it. This is public verifiable record of all the transactions or events that happen and the auditable history of usage. So I can take information that I know about an artifact that's been signed, let's say using a cosign, and I can go to the transparency log, right? So you can see that Record provides that. And we then upload that to the transparency log, the X509, and we can see that it was signed. So this helps us prevent any unauthorized use of keys or inappropriate signing, right? We can identify any sort of suspicious activity. So let's say someone gets a hold of one of these short-lived keys and tries to sign something, we can see that in the transparency log. And we can take necessary actions to make sure that, well, if someone issued a short-lived key, maybe they are logging in as with my identity provider, right? Maybe they've compromised my actual OpenID Connect identity, and I'm going to need to take steps to secure that. Hopefully that doesn't happen. But by having that transparency log, we have a record of all the keys that were issued, all the signatures that were issued with your identity. So we have strong integrity guarantees that are provided by the transaction log and the SigStore ecosystem, right? So there are a couple ways that we can validate a signature, right? We can search let's say we're using the public Recore transparency log. You can go to search.sigstore.dev and you can go and find a record, right? So you can use someone's email if that's the identity they use to log in. You can use the hash. You can use the commit SHA, the UUID of that entry in the log. You can use the log index, right? It starts from 1 and just counts up. So if I have any of this information, I can go to the search console and I can search that, or I can use a command line tool. So this is an example of the Recore CLI, where we log in to our recore.sigstore.dev, just basically logging into the CLI for validation. Okay, so that is kind of the future when it comes to making signing easier, right? We want to be able to not have to worry so much about key management and use identity systems that are already established. And we can do that through SigStore. In the lab, we'll work with cosign to sign a container image. So we're getting close to lunch here. You got mic set up. Give us a moment, folks. We're going to transition. Yeah, exactly.
Perfect. This next lap will be pretty short, so bear with me as I refasten. There we go. Thank you very much, Chris. Looks like I've got my levels all good to go. Yeah. All right. Oh, yeah.
We're good.
Yep, I think I'm good.
I'll let you set that up.
Yep, sounds good. So, welcome back, everybody. It's me again. Hi, again. So, let's go ahead and take a look at some keyless cryptography, some artifact signing, more specifically, some containers. A lot of people use containers these days. So, that is what we'll be taking a look at next. Let me just get my terminal back up. All right. All right. So in this next lab, we're going to be working with Cosine, and that's going to be the project that Chris was talking about. This is a combination of I pronounce it Fulgio for some reason. I'm not sure why, but I call it so it's a combination of yeah. So so we're going to be installing Cosine, and so Cosine is actually specifically for containers. Cosine. So that's going to be what it's primarily going to be for. So in the lab document, we actually install it. We're going to be installing it via the deb file. So we're not going to bother with things like adjusting apt. We're just going to go ahead and install the deb file. So we download the latest version. And then once we've downloaded it, we're going to use dpackage to actually install Cosine for us. Okay. So I actually have it already signed or already there. So we've got Cosine now up and running. So at this point, what we'll want to do is actually go ahead and make sure that Cosine is running. This shouldn't take very long. So Cosine version, we've got that going right there. So now we've got a tool that's going to make it much easier. And that's one of the things that Chris talked about. It's the fact that as you saw me in the first lab, there's a whole lot that I was doing. I was like making a key. I was going to go export the key. I'm going to go ahead and do all sorts of stuff. And I even mentioned about, hey, you might have to make this big old package that you have to re-download all the time. In something like Arch Linux, that's fine. I use Arch, by the way. So with that being said, it's really just making it easy. That's really instrumental in making all of these practices much more widely adopted, because if it's hard, you're not going to do it. And I believe it's basically, if it's hard in any juncture, any kind of juncture, then somebody's going to be discouraged. At least the least dedicated to the attack would be discouraged. So and that also goes for best practice too, or new practices too. So we've got Cosine going. And so what we're going to do is first we need to generate a key pair, and that's going to be the ones that Cosine is actually going to end up using. So Cosine is actually, these particular keys are going to be what will be used to actually generate our signing keys, the short-lived ones that Chris had spoken about. So once we've done that, we're going to use Cosine generate pair. Again, it's making it easy. So it's going to be much, much easier to just say, okay, let's just use the tool to generate all this stuff on our behalf. So I already have those all signed up or all set up. So if I look around here, I should have my Cosine keys right there. We do ls -l, and we see I have a, this key specifically is for, again, creating my signing keys, those short-lived ones that are going to be the artifact that I want to sign. Question? Okay, sorry. All right, so next we need to go ahead and create a container image. So in our case here, what we're actually going to do is we're actually going to create a Docker image. And from that, we're just going to do that from our main Go. That was the one that we created a little bit earlier. So we'll containerize it. It's just going to be running Golang 1, 2, 3. This is going to result in a really big container, by the way. Golang 1, 2, 3 is just a monster in terms of file size. It's like 800+ megabytes. It's awful. It's not, well, the size is quite awful, but the Golang is cool. So we go ahead and we actually build the Docker image. And so we're going to let our little T3A small build that. Should take about 30 seconds, just about. Yeah. Oh, am I still sure? Oh yeah, sure. Sorry about that. All right. So yeah, okay, cool. So I am screen sharing. Cool. All right, so we're going to sudo docker build image build. I actually already have that built. I actually just rehearsed the lab prior to this. So if I do a docker image build right here, if I do a control R here, image build. All right, and we'll go do, docker image build, and I'll go ahead and just run it from the instruction here. You're going to see it actually build. For me, it's just going to be all cache because I've got that all set up. Control C, there we go. And then Command V, there we go. That's incorrect. That's correct. All right, cool. So naturally, I have to go back, go to a Docker image. All right, there you go. So it's already been cached. I've already built it. So once we have it, as Chris said, you do need something to sign. So we looked into signing a Git commit, and the whole point is, again, to ensure that once you've received that particular commit, that particular artifact, you can verify who actually did it. And again, that's becoming a more common practice, and it's a requirement in many open source projects. So for this one, obviously, we want to just make sure that the image actually runs. When I was testing this, when you first run this image, by the way, it's going to take around 30 seconds. There's something in the code that actually delays the actual listening by about 30 seconds. So do pardon that. If you end up seeing something like, well, actually, you actually got to run it. But if you end up seeing something like container isn't even running yet, it's because, well, it's not quite there yet. So we'll see here that I'm just going to contact the IP address of the RxM cosign container, and it's going to say, I'm not listening yet. Again, please wait about 30 seconds. It will eventually get back up. And actually, you can confirm that with sudo docker logs on RxM cosign. Yeah, and basically what we're really going to be watching out for is that listening on port 80 part. So once it's listening on port 80, Control C, there we go. Then we should get the hello worlds. Okay, so we have our container image. And so let's go ahead and start pushing it, shall we? So first off, we generate the cosign key pairs and again, these are the ones for generating those short-lived key pairs there. And these are the ones that we're going to be keeping around ourselves. And you can do that with a KMS. And of course, you can provide a password if you want. Highly suggest you protect it some manner. And so now we can go ahead and sign it. So in order to sign our image, and again, since I just did the lab here, in order to sign the image, we actually have to sign the SHA digest. Now, the SHA digest, you can think of that as kind of the global ID that is assigned to a particular set of image layers, or rather an image hash. And you only get a SHA digest once you've done a push to at least one registry. If you just create one, you don't have that. All you have is the image ID, which is the local ID. Think of it that way. And so in order for us to have that signable hash, we actually have to make sure that we have that SHA digest, excuse me. So we can see here that, hey, you can't use a tag when you're signing with cosign because they want you to be very specific about what you do sign. So what we're going to do is you can see initially, you're going to see that you don't have that digest. Again, it's because it's just been created and it doesn't have that global ID, that SHA digest, to be globally identified. So what we're going to do is we're going to trick it. We are going to launch a local container registry. And in that local container registry, which will serve at port 5000 on our local host, and we'll be able to push it to localhost 5000. Docker is actually going to allow us to do that because it's not an IP address, at least. We have to do a bunch of other tricks for that. So once we have our container registry running, we want to make sure that we have a name that will actually push over to our registry. Now, for those of you that are unfamiliar, what goes into the container name is the following. You're going to have the address of the registry that you want to push to. Registry being that network service that you're going to be using, that you're going to upload or push to as the developer, or download, or rather pull from as a client. So the image name is going to state where you're going to get it, and that's going to include the registry address. Next is going to be the repository within the registry. This could be a user's directory. This could be just the programs directory. Either way, it's the repository within the registry, or rather the directory within the registry, followed by the tag. And that's going to be the very specific version of the container image that you want to run. And typically you end up with a tag for each minor release, major release, etc. So by assigning another tag to this particular image, basically what we're doing is we're associating that set of layers of the image with a brand new name, And this particular name points to the local registry that we just created. Right, so with that, we're going to go ahead and push this. And again, the hello world image that we created is rather big, so this might take a little while. It took me about a minute or so. It's 800 megabytes, so it's quite a bit. So we'll push that over. We'll wait for that to happen. And then once that's done, though, you're going to see that now a SHA digest has been assigned. So this one I can show. So if I head on over to my terminal, clear things up, you can see here that now I have a SHA digest, and this SHA digest is the one that I want to go ahead and sign. So with that being said, and by the way, in the document, this is what we're going to sign: the SHA digest, global ID, this image ID, this is the local ID. So we need to use this SHA digest in our signature. So to make this easy on us, we're just going to export it into a environment variable. And then now we can actually go ahead and use cosign sign. And you're going to see that it's not going to error because now it actually has a digest to go ahead and do that. And the reason that you don't really have that particular permission to just push to wherever is because when cosign signs it, it's going to push the signed image back into the container repository. So again, you're attaching that signature to that SHA digest. So then that way, anyone that needs to look at it can verify that. And so part of this, and again, in the theme of making this easy, part of this is the fact that when you say yes, what you're basically consenting to is the fact that you are recording this transaction to a publicly available transaction log. That would be Raycore or Raycore, whichever, Randcore, whatever. No, it's Raycore, excuse me. So with that being said, of course, you might have already put in a password for your private key. Naturally, this is because there has to be a new set of certificates assigned by Fulcio. And so in that case, that's why we're entering the password for the private keys, so we can actually generate those particular keys for use for signing by Fulcio. And ultimately, that's what's going to be recorded up in the Raycore transaction log. So with that being said, we go ahead and allow it. We're going to see that a new transaction log entry has been created, and there actually is a publicly available Raycore instance in which you might be able to find your particular transaction log. I might have that next time I'm up here after the last lecture. So again, cosign, making it easy. So it's not just making the signatures easy, but it's also going to be the verification. So we can use this handy cosign verify, and we're going to be verifying against the public key, which maybe we'll go distribute our own, or maybe put in some sort of metadata store that our service can actually come up into. And so we're going to then verify the signature attached to this particular image, and we're going to see the various checks, such as the cosign claims being validated. Yes, it was signed. This is the transaction log. These were the certificates that were used to sign it at this given time. And of course, those are going to be all the things that can help you establish that. And so let's say, for example, you've got a CI/CD pipeline, continuous integration, continuous deployment, or delivery. Let's say that you implement cosign as part of that CI/CD pipeline. And let's say that the condition for allowing that image into wherever you're pushing it to or deploying it to, let's say that cosign has to succeed for that to happen. With cosign, that can be quite easily done because now you're making it a part of that CI/CD, specifically the CD part. And that's going to make it much easier for your automated systems to actually verify that. And then ultimately, I'm sure someone has to, click the button to let it through, but that's going to be part of the CI/CD process there. So with that being said, what we've done so far is we've verified a private image, but what about the public image? Well, the thing is, we actually end up having to pick up the public key. So this is something that, again, you will see pretty often. I'm a little loath to add another tab to Chris's browser here, but basically, oftentimes you will see that next to the binary download that you want, you typically end up seeing some sort of download link to either the public key or even a file containing the SHA hash. Basically, it's pretty common practice for a public key to be published alongside an application just to make it easier. All right, so some food for thought. A little bit of a release example or real world examples here. So we've got Kubernetes release artifact signing. I'm going to go ahead and just open this in a new tab right here so I don't mess things up here. We can see here that that Kubernetes, the Kubernetes project actually does end up using cosign, and you can absolutely use those. And so what you will have to do is actually download the signature file right there. And once you've downloaded the signature file, you can go ahead and use cosign verify, or rather verify blob. And that is going to be how you could potentially use cosign to validate a publicly available image. And just the fact that a project is willing to publish their public keys, that's typically a decent sign that, yes, this is a legitimate outfit. They're the ones that are, they are the ones publishing this, and they are providing you with the means to do that third-party verification. After that, we go ahead and clean up, and that is the lab number 2. Were there any questions? I kind of motored through that real quick. Question? The keys? Yeah, so the question was there a server or some sort of service for cosign, or really some other kind of verification tool to do that? There are tools like that. What was it? Typically that falls to the responsibility of something called a metadata store. A project that comes to mind is Graphias or Open Metadata. Basically, these types of services exist for holding that kind of information, things like public keys, or maybe just other kinds of metadata, timestamps, things of that nature. And so that would allow a project, let's say it would allow you to at least download it from a central source, if not, or it might even go as far as having an integration with the program and actually allow you to state, hey, connect to this metadata store, the key is in there. And so it could potentially use that central source as that distribution. Yeah. Question?
Yeah, what you saying that the public key usually following
so the question was, what would reduce the suspicion that that's the actual like key? Is that correct? Yeah, so that one is a tricky one for sure. So in that case, that's a pretty good one actually. Chris, you gotta. Yeah, so basically what is preventing someone from publishing a bad public key as part of their part of a release for a program? Would you have any?
I don't know. I'm not really sure what you would achieve with that. Only because I'm not sure why you would want to do that. So the whole point is to have someone trust you, right? So if you release a bad public key, then
the other way, I want to download that's public key.
Yeah.
What is that public key? Different than one.
okay, so if the files were signed with a private key, the pair has to match, or it won't validate the signature. So you can't substitute some fake public key in place of that to try and spoof the verification. The second step, especially with SigStore, is it's in the transaction log. So that key and Fulcio in the CT has a transaction about how that key was issued, and that key has an ID, and so that's not going to match either. So there are a couple different, ways that the transaction log prevents that, right? You can't substitute a key, and the ID won't match with the original key. So, and then 2, when you try and validate the bits, someone tries to validate the bits with a bad key, it's not paired with the private key that was used to sign it, and so it won't validate. It won't work that way. So yeah.
I actually have I recall an anecdote actually. I think Ron, you actually opened this with Kubernetes one time. They had I think it was one of the releases for 1.24. I hate to call them out like this, but they had a release, one of their releases where they they publish SHA hashes, and one of the files,
Shaw was, Shaw got used on everything.
oh, yeah, so yeah, so basically what ended up happening was they published a bad verification artifact, in this case the SHA, and basically we had to open, what did you end up doing? Like you opened a ticket with?
Yeah, for the ticket.
Yeah. So
Oh, yeah, maybe else.
yeah, sure.
Um,
Yeah, you're on that.
yeah, so nothing crazy. It's actually something, I will say this, I'm not an elite hacker. I just noticed, when anytime you make an artifact, you should, make a hash, write a SHA on it to make sure it's not been tampered with. I went out to the release artifacts for Kubernetes, and every release had the same hash, which is, unless we're all using the same build every time, is impossible. And there's a hacker website, like you report, not hacker, but the report bad things, and you get a reward if they
Bounties.
Yeah, so I submitted to that. They've talked to them, and then they looked at me. They're like, "Oh, that's not a real hack. We just messed up." So I never got my $100 for reporting it. But yeah, that even the basics, like that was probably one of the most basic things you could mess up, and it was messed up, right? So it's very easy to mess up security, anything. So it's very hard to do.
Appreciate it. Thanks, Ron. Yeah, I just remembered that. Thanks for asking the question.
That question is where what is the public key that goes with the can be hacked, right? What if the public the key that goes with the container image, if it is in the same location, what if it is changed? Then that makes it that it cannot be verified at all, right? That's the downside of it. So can that be an intentional attempt to do so that, say, for example, a Kubernetes container image, which is widely used, cannot be verified now at all by, so will it come under not best practice to have the key along with the image itself?
Yes, that's correct. So hopefully you folks online caught that. He was talking to the mic there. But basically, yes, the attack there in that sense would be you're trying to undermine the trust in that particular project. You just inject a bunch of bad keys. By the way, this is not an instruction. So you're going to inject a bunch of bad keys, and then all of a sudden, let's say you have a bunch of automated tests that start failing because, hey, now we suddenly can't verify it. So then that's going to, it's almost like a denial of service if you think about it, because now the folks at the compromised project have to take time to actually figure out, okay, what happened to our public key, and that in itself can be kind of an attack. And this time it's not on the code, it's not stealing the code, it's attacking their trust. Now, why someone would do that, not quite sure, but that's, at least in my brain, that's probably something. Okay, let's say I was red team, that's probably something I'd do. Question.
I came for a high level understanding of encryption, and I found this really good. But I had two questions. The first is, what is the relationship between the private key and the public key? And the second one is your thoughts on GitHub being hacked about 10 years ago, and they downloaded Nissan's EV software, proprietary software. And how is that possible?
Right. So again, they were speaking to Mike there. So the first one, with regards to the relationship between the public key and the private key. The private key is the one that you would typically use to either do the signing, or you would generate your keys from there. So that's the one that you really want to protect. That's the one that you establish trust with. The public key, excuse me, sorry about that. The public key is going to be that's the one that you would distribute, and it is related to the private key in the fact that anything that the private key has signed or encrypted can be decrypted or verified using that public key. Is that clear? So
it's a more generic version of the private key, or it's a more generic version of the private key, or is it the other way around? I presume there's a mathematical relationship.
Yeah. So in that case, it's there's a difference in the functionalities as well, because with a private key, you can potentially generate, whereas with a public key, you can just decrypt or verify. So that's one of the more fundamental differences between the two. And this, again, I keep repeating it, but it really is important. You want to protect that private key because that is your trust, at least for that particular one. If it does get breached, that's where you have to go through the song and dance of, oh, I need to revoke my private key, then I need to regenerate a bunch of other stuff, and I have to basically take time to reestablish that trust.
Again, the idea with SigStore is you don't have to manage that anymore, right? You want to use short-lived keys. We already kind of do this in a lot of continuous integration systems where we provide a temporary key to a build system like Jenkins or Tecton or something, so that it can temporarily build something and sign it, and it's short-lived anyways. But for this, in this case, sorry, Ron, I know I'm kind of off camera over here, but hopefully folks can hear me. But in this case, SigStore aims to remove all that complexity so that you don't have to manage a private key, that the keys that you use to sign artifacts are short-lived. And like I said, a matter of minutes, so that what you have to manage is your identity, right? And of course, as a user of systems, you're going to protect your identity, right? With all the systems that already exist, right? Your organization's going to protect your identity and going to require you to do 2FA, right? So that you present something that you know, present something that you are, and that way your identity is protected. You don't have to worry about managing a key. So ideally, we simplify this into using our existing identity systems and not have to worry about managing keys so much, right? And that's why that transaction log is so important with SigStore, because then we have a record of who I was when I signed an artifact, who I am, and I prove that I'm this person and I did this act, I did this act of signing an artifact, right? As for the second question, I'm not as familiar with I can't say I can answer that question.
Yeah, with in that case, so yeah, definitely. But just in general, where breaches like that are concerned, where some big service gets hacked and your keys are all over there, then you're the one on the hook to have to go through, regenerate your private key or regenerate your public keys, and just and again, you have to reestablish that trust. So it can be pretty annoying for sure, but it is, in general, if your keys get breached, you have to regenerate them, and you have to send out several embarrassing emails to do that. Not that I've never done that before. It's just, it's definitely inconvenient.
So basically what happened was that they had accidentally made their private key available to outsiders.
Yeah, that's really bad, because they can generate additional signing keys. And I think something similar might have happened to one of the big certificate authorities out there. I think I don't recall which one, but the certificate authorities, the ones that handle things like browser certificates for HTTPS. If someone, there's the same concept exists for certificate signing. Basically, I think there was a root certificate that was compromised, and that was a big hack. I just can't recall exactly who it was, but basically what ends up happening is that, again, that particular company ended up having to do all manner of, I wish I could speak more specifically on that, but the same dance applied. They had to regenerate their private keys and redistribute all those. It's pretty inconvenient.
Thanks.
One last question.
So in this lab, we installed cosign into the VM, and then we did the signing of a registry that is created locally, and we did the verification. So how does it work on an enterprise software where we have our own service? We would have to, the current flow is that service gets built into an image and then pushed into a container registry, which will be consumed by another service. And then in that flow, where would a cosign and other like record or other related services or frameworks reside? How does it work? Can you just give a quick walkthrough of how does it work?
Yeah, sure. So, yeah, sorry. So with regards to that, again, hopefully folks got the question there. I saw the mic bouncing. So an example workflow would be, let's say, in a workflow where you're building the container there, let's say you have the initial build, and then you have maybe container scanning, other kinds of security that happens. So once, after the containers have been scanned, and let's say pulled back to another system, that's where, and this is where I was talking about the CI/CD part, the automated pipeline comes in. So between the finalized container being created and being sent out to the public repository, the public facing one, then what you would want to do is you would have your step of have a cosign step. And that could be as simple as, let's say in Jenkins, for example, you just set up a bash script that just runs cosign sign on that particular SHA hash, SHA digest, excuse me. And then from there, you basically integrate it as that last step prior to publishing to the public, to a public facing registry. Does that make, is that fun?
The pipeline agent machine that does this can have cosign install and it does that. But how about the verification part? Where will, because the main purpose of this is to not manage private and public keys independently and not distribute and cosign. The SIG store will take care of it, right? So I'm trying to understand here, yeah, we install cosign and then we do it. But there should be a common central place where verification also, because we need to use the public key for verification. So my understanding is SIG store abstracts that out. How is it achieved? I'm trying to understand that.
So you're still having to, you still have to generate the keys, of course, right? Through cosign, yeah. When you do verification downstream, usually your orchestration system handles that. So if I'm going to deploy a replica of my microservice, I built a container and we did all the security scanning. There's no CVEs or anything. We signed it, right? We used the short-lived keys from cosign. Downstream, I want to distribute that. Well, how am I doing that? I'm using a system like Kubernetes to distribute that. Kubernetes can hook into systems like Opa Gatekeeper, Kyverno. What they use is what's called a validating admission control webhook. What that does is it calls a webhook to a system and says, a user is trying to deploy a pod in Kubernetes with this image or from this image, right? Is that image valid, right? And it can go through that policy engine, and that policy engine can then determine if that image is valid and then tell Kubernetes, yes, it's valid or it's not, right? So usually it's through several systems integrated together, right? So Opa Gatekeeper, Kyverno, those types of systems can do that type of integration, either using keys or using SIG store.
Using cosign, you will generate a key pair, and then that can be pushed into key vaults or somewhere. That can be used by systems further down the line for verification, and then it is pushed to the registry now. And then before the deployment happens, the verification can happen that, okay, this is actually a signed one. During the deployment time, we would get from the same key vault.
Sorry, I want to wait.
Yeah, during the validation again, the system who before the deployment, the Kubernetes system can be used to get the public key from key vault that was pushed during the initial phase, and then it can verify that, okay, it is in fact nothing got tampered in between where it was pushed and then the time it was getting deployed, right? Is that flow correct?
Good job. Did you want to do the next? That was a perfect explanation.
Oh, okay. Okay.
So my answer is yes.
Okay.
Yeah.
Okay.
Yeah, that's the idea is that you have systems that can verify an image before it gets deployed.
Present a system are how is it? What are the other ways of doing it because I'm not too familiar how it happens in our company or in our project. But what is the alternative way to manage everything separately? Because now only part is even now we have to distribute the keys, right? It's only that using cosign we generated, but we have other key gen tools. We can use that and then distribute, right? Yeah, content trust.
Yeah, a long time ago, I watched a talk by Dr. Justin Kapos from NYU. Highly recommend listening to anything he says about on this topic because he's the guy who created In Toto, which is something we're going to actually talk about in the next section and use. But it started with like a system called Content Trust that allowed for verification of images that were signed. It's kind of a long history that dates back to like 2015. But in terms of, I think part of your question was you have disparate systems that are using different keys for different use cases, like you're using a GPG key for signing commits, and you need to be able to, someone needs to be able to validate that commit, right? And then you also have cosign that's being used for container images, right? The idea is to unify all this stuff too, because as you saw when I was talking about in the lecture, we have cosign for container image and we have git sign for git commits. So rather than using disparate systems, you could have all the developers could use git sign, and then that's all gets recorded in all the SigStore transaction logs. And then when the software is produced through the CI systems, we can generate the cosign keys and all of that through SigStore too. And then you have one central place that you're managing both commits to code bases and distributed software once you go to send it out into a Kubernetes cluster. So I will say this, yeah, that it's a work in progress, right? None of this stuff is fully complete yet, right? We're going to talk about frameworks and thinking about how we communicate how ready we are to do these things. And the whole reason why we're here talking about it is because it's fairly new, right? It's not everything's been solved yet. So it's a community effort and more help is needed. So yeah. Yeah.
Okay. So that's the end of the second lab.
Yes.
Right. So great questions. For the sake of being on schedule here, originally I believe our lunch was 12 to 1. Leor, do you happen to any news or? Okay. Well, we got a couple things to do, but so it looks like food will be here at 12:33. So 12:34, there's going to be chaos. Chris, do you want, how do I get back to the presentation?
Just the other tab.
Sorry, not my glasses. I added a slide for your.
Oh, here. Yeah, you got it. You're good.
Okay. How do I go full screen? Yeah. Okay, so first, Frontegg, our wonderful food sponsor, Leor is here to tell us more about Frontegg. Leor, would you mind? I tried to do it justice, but you will do it more justice. So yeah, I got this slide and then the next one's the QR codes.
Okay, and then should I hit or you'll?
Yeah, just hit down.
Yeah, okay, all right. Hey guys, hope you're enjoying everything today. The great workshops and the food. Hope you enjoyed the breakfast as well. More on the way. So just a few words about Frontegg. So I was very curious about this meetup. All of ACM's meetups are great. Okay, let's start with that. But this one was particularly interesting to us because we are a customer identity and access management company that makes sure that all of your logins and authorization are as secure as can be. So obviously there's encrypted technology there, but it's one more way that you can make sure that your tenants are secure. So what we have is an out-of-the-box solution that allows any company to essentially deploy logins, MFA, SSO, as well as authorization for who can see what once they're in the system, right? All of that out of the box, low code, so that developers can manage authorization and authentication, but also non-developers can have an influence on the parts of auth that they care about. So InfoSec products can also get in on the mix, also can play a role, and this saves developers so much time. Identity management is not the priority for most developers. They'd rather be building their next cool app, and we make it possible for them to get back to doing what they love and save on that frustration of developing identity systems in-house, which is what companies often do when they're first starting out. So that's us in a nutshell. We so here, if you're curious to learn more, we have a one-pager that we have a QR code, and also you can sign up for free. So we're basically free forever for startups. So if you have under 50 tenants, meaning we support companies that support companies, we're B2B primarily, though not only. If you are a company that supports companies for authorization and authentication purposes, and you have under 50 tenants, under 7,500 users, will be free for you forever. Once you scale, we scale with you, and then there's a cost. But the amount of complexity that Frontegg is able to handle is beyond anything that can be developed using open source technology. So it's really a scalable solution and can be used by non-developers. So helping developers get back to what they love to do is our philosophy and our mission.
Round of applause to Frontegg. Thank you, Leon. Frontegg has been very good to the ACM and now to the ACM and the Internet Society. So thank you. All right. Next, you may have seen it, depending on when you came in, that our friends here at the Google Community Space have put on an exhibit. David is here to tell us a little bit more about it, and hopefully you will try it out.
Yes. We want to thank Google for allowing us to host this event here. Also, as a part of the experience that's happening, at the entrance, as you came through, the Google School for Leaders, which is Google's internal leadership development training team, has created a unique exhibit for us to experience. It is a new take on the future of the library. So think of it as a new immersive take on the traditional library and a way to approach finding new literature for you to read that you're interested in. It's their first time popping up, and they would love everybody's input. So this is your chance to kind of experience a prototype in its early stages from Google. Thank you.
Thank you, David. Okay, so yes, please try it out, especially after the Internet Archive got hacked 3 days ago. You know, our libraries are under assault, so try this one, see how it goes. So at this point, and Chris, correct me if I'm wrong, I think we'll go ahead and break for lunch. I know food's maybe still 10 minutes out, but give you a chance to stretch and whatnot. Real quick, just on logistics, as you know, there's a second track that's at Cloudflare. So Cloudflare, about a 20-minute walk, just down the Embarcadero to Townsend, take a right, and you'll run into it. We want everyone there. And in fact, there's a couple of panels where we hope our members here will join us from the crowd to make it pretty lively. We have some of our speakers here as well, hanging out with us. And we really hope to make it engaging and really hope everyone can make it. So I know this goes after that starts, that's okay. The bulk of what's happening, the prime time, we'll call it, starts around 4:30 over there. So, you know, may just be a few people at the start, but please come after this. We want you there. Oh yeah, I want to do it now or after? No, we'll do it. Okay. Anything you want to say about it? No. We have a giveaway after lunch. Our first giveaway for the open enrollment. We'll talk about it more after lunch. So thanks. Enjoy your time. We're zooming an hour, and I think that's it.
Okay, so we're done with what we were doing in the room here. We're going to go ahead and start up for folks that are online. I will share the screen again here, and hopefully we should be good. All right, so hopefully you can kind of see where we're going with a lot of this, because we talked about key management. We talked about things like signing Git commits and signing container images. And really, this is all about producing software, right? And doing it in a secure way. So we just want to talk about some of the concerns and just kind of codify some of these concepts and talk about software supply chain security, some of the challenges and some of the places where cryptography plays a role in supply chain security in general. There we go. So we can think of the supply chain like a traditional supply chain, right? Where we're trying to produce a product that goes to a customer, right? So your traditional supply chain is at the top of this example here down at the bottom. Well, software is delivered in the same way that a product is delivered to a consumer, right? We have source code, we have dependencies, we have systems, so basically raw materials, right? We have build systems or engineers that build the software, just like we have factories that produce products. We need to be able to transmit those artifacts or the outputs of the supply chain to some place that they can be distributed. So in a traditional supply chain, if this is a truck, right, going to some store. In software, of course, this is typically over a network and a network-based server, right? That is an application repository. This may be someplace that we store a binary or a jar file or a container image, so that it can then be pulled by downstream systems so that they can be deployed. Typically in cloud native, this is on a Kubernetes cluster. And so any place along this path can be exploited. And the idea is that if we can get as far left up this chain as possible and secure everything from the raw materials down, then we can avoid some of the things we were talking about earlier, issues with losing trust from our customers and monetary losses, right? We want to avoid any software that contains malicious code or active exploits or even just known vulnerabilities, right? Again, we talked a little bit about this before. It's an extensive problem. This is aspirational. Not all of this is complete yet, but it's a way for us to have conversations about how we improve in the community. So here's a example of an attack, right? An attacker doesn't have to compromise a consumer if they can compromise that consumer's vendor. And oftentimes they can actually derive more value out of attacking the software supplier than they can from just attacking the organization directly. Because if we attack a supplier, typically that supplier has multiple customers, right? Multiple consumers. And so by injecting some malicious code, as you see kind of in this chain, right? We have commits that go in. We've got Jenkins, we've got stuff being built. This is Go code. And then somebody injects this malicious payload in there. And then that gets distributed and gets down to the customer's private networks, right? Not just one, but plural. Then the attacker never had to make a direct attack against the end consumers and can compromise many of them, right? Because a lot of people are consuming this software. And so now they can compromise a lot of consumers' internal networks, right? That means it can infect servers, workstations, containers, allowing that container to get a foothold inside that network and start to expand that footprint, right? Discover the networks that are there, discovers the servers that are there, discover the data, and try and exfiltrate that data, and then use it for ransom or whatever other malicious activities that they want to do. Right? Interesting statistic from Gartner, right? They predict by 2025, 45% of organizations will have experienced a software supply chain attack. Because software is everywhere, as we well know, right? Companies that aren't software companies have to use software, and they often have to rely upon their vendors to provide secure software. And if we're not doing that, then they're open to attack. Matter of fact, this is sort of the basis of the SolarWinds attack, or the SolarWinds hack, so to speak, right? The idea was that attackers compromised SolarWinds build systems and didn't exploit the build systems to try and compromise SolarWinds. They started injecting malicious payloads into the final product so that they could then compromise SolarWinds customers, because of course there's lots of SolarWinds customers out there. And one of those customers, of course, was the US government, which then was compromised for a number of, well, longer than they would have liked to be, right? So this is where the government decided that they would start to require minimum standards for software that they were going to use. So for a very long time, government agencies have had the requirement that they need to rebuild software, that they can't rely on pulling in dependencies, pulling in binaries, and from sources outside the government, because that leads to compromise, which meant that the government had to move a lot slower than industry, because they had to rebuild everything from scratch to make sure that none of it was compromised, right? In the open source and industry, we don't do this a lot, right? We don't necessarily always rebuild all the dependencies, but we may be at a lower risk, of course, than a government agency. But it means that the government has to move slower, and they want to work with the community to improve security, shifting some of that responsibility into the open source communities so that they can use software securely. And as a result, the rest of the community can use software securely, right? So one of those things is a software bill of materials. Another one of those things is an attestation. So we attest that a particular activity was done. What is that activity? It could be cloning a Git repo. We want to ensure that if we're cloning a repo, we only clone that repo. And if someone injects a change, cloning a different repo that includes a malicious payload, that is detected and the signature is invalidated, right? So we're expanding this to not just artifacts, not just container images, but all the activities related to a software supply chain, which means that every activity that we do becomes signed and is verifiable. And so, again, this is a really complex problem and it's aspirational, but if we can start to think about what are the aspects of the software supply chain that we need to secure, it'll help us kind of break down the problem, right? So one is securing the source code, right? So this can be the first party code produced by someone who's creating software. Materials, this is again the raw materials that come from third-party codes, the things that we pull in. Now, right now, you may pull in some third-party code or some dependency, and you're not able to verify it because that upstream provider of that raw material, so to speak, doesn't provide any sort of attestation. They don't have an SBOM, but the idea is to try and encourage people who are doing this to adopt these practices and start to provide provenance of everything that we're building, right? Securing the build pipelines, this means hardening so that we have hardened build platforms that are isolated from the network and use verification, right? That we're verifying the source code is signed, we're verifying the materials are signed. And if we don't, if those things fail, then we fail builds so that we don't build artifacts that have malicious payloads or known vulnerabilities. Second to last one here, securing the artifacts, right? This is exactly what cosigns is about. Making sure that when we produce a software artifact, oftentimes in Cloud Native, that is a container image, that it's signed, and we provide a way to verify it. And then lastly, securing the deployments. We talked about this too, being able to hook in at the deployment phase, verifying everything upstream to make sure that we don't deploy an artifact that might have a vulnerability. And this could happen just because we built the artifact yesterday or last week, but now there's a known vulnerability that got discovered today, right? Just because you built something a few hours ago doesn't mean that something was discovered by some security researcher or was published. So we have to make sure that we're constantly verifying before we take that artifact to production that it's still secure, right? Because secure today is only secure today. Secure in this hour is only secure in this hour. We have to make sure that we're constantly paying attention to this, right? So how does cryptography play into securing the source code, right? So initial step here is establishing and ensuring the integrity of the source code, right? So we've done this. We practiced this in the first section, verification, requiring signed commits and tags, right? We can use keys, GPG keys, we can use git sign to sign commits so that we know that the author of the code has produced that code, and we can verify that it hasn't been changed in any way, right? In terms of automation, we need to prevent key material from getting into source code repos, things like credential files, SSH keys, tokens. So we constantly want to scan our Git environments for rogue secrets and make sure that they don't get committed to source code repos. Now, there is some software that allows you to commit secrets. There's a piece of open source software called Sealed Secrets. This is a great piece of software that allows you to upstream encrypt a secret so that you can then commit it to Git safely. That's a piece of software that's used in open source that a lot of people use. When it gets then pulled downstream into production, we then decrypt it and we can use it as a secret. So either we completely avoid committing secrets to Git, or we use a system where we pre-encrypt before committing. In terms of secure authentication, we use things like SSH keys so that developers have access to source code repositories. We need to have rotation policy so that we do not have long-lived keys. So hopefully you can see some of these things kind of tying into the ecosystem improvements that we've seen, right? Keeping short-lived keys, credentials for service access, and even, in the case of SigStore, short-lived keys for humans, right? When we're going to sign something, we use short-lived keys as well. So if we can get as close as we can to the shortest lifespan of keys, then we can avoid any attacks that involve key compromise. In terms of securing the materials, again, I'm highlighting the things that are specifically because we're Global Encryption Day. So I want to make sure that we really focus on the things that are related to cryptography, right? So there's a lot of other aspects of securing the materials, like verifying dependencies, scanning for composition analysis, those sorts of things. But when it comes to cryptography, we want to produce a software bill of materials, and we want to sign that so that we can say, this is the everything that makes up this piece of software, right? Think of it as a list of ingredients for software, right? Just a big list of everything that's included in a piece of software, right? So you've got libraries, operating system tools and packages, other dependencies. We want to make sure that we're transparent of all the things that we're using in a piece of software. And then we make sure that we sign that. Because again, someone could alter that SBOM without a signature and then inject their own malicious payload. And because it's in the software bill of materials, we think, oh, well, that dependency is legitimate because it was in the software bill of materials because someone altered it, right? With a signature in place that can't be altered, we can detect that change. And that's only possible through cryptography, right? So that allows us to transparently tell consumers exactly all the pieces that are associated with whatever we're building, whatever that artifact would be, right? Now, when we talk about the build pipeline, we want to, again, a lot of aspects here that are associated with hardening the build pipeline. This is a challenge because if I want to get to the point where I can provide unfalsifiable provenance for an artifact, then I have to do a lot of things. Harden my environment against network connections, do everything as infrastructure as code so it's repeatable, make sure that the outputs of one step are verified as the inputs of another step. And so, again, that requires signatures because I need to be able to validate that step one, git clone, I sign that, I verify it, I validate the signature, I validate the checksum of the artifact that's passed to step two. So if step one is clone the Git repo and step two is build the Docker file, right? Before I build the Docker file, I need to validate that step one was done correctly and that Git repo was not changed, right? The URL of that was not changed. The only way to do that, to validate the signature, make sure that the checksum of all the dependencies before we ingest them in a build stage, right? In terms of securing the artifacts, everything we produce, right? All the metadata, all the intermediate artifacts associated with the software supply chain needs to be signed. There's a lot of signatures and a lot of verification, right? But in order to have unfalsifiable provenance, this is what we need. We need to be able to distribute that in a way that's easy for consumers to verify these things downstream, right? Which means we have to have some sort of service where we store that metadata. Hopefully you can see, right? Using like Recore and using an OCI registry where I can store metadata, I can store my artifact, I can store the signature, and I can store the SBOM there, means that I'm not making it difficult for the downstream consumer to try and validate all this stuff. Because if they have to go to 5 different resources to get it, that makes it just more difficult before they use and deploy it, right? So in terms of securing deployments, right, we want to make sure that clients can perform verification of artifacts. And we really want to do this in an automated way, right? This is not something where we're involving humans because that slows down the build process. And we're, again, the weakest link in the chain, right? We want this to be done programmatically. So if we create SBOMs, and we should, we need to make sure that the signatures are verified. And the keys has to be validated belonging to an authorized party. And we also need to verify the freshness of files because we could sign an artifact. And that artifact, let's say, has a valid signature. But then, as I mentioned, that's only valid until the next vulnerability is found with that artifact. Okay, so we reproduce that artifact, getting rid of that vulnerability. But the old artifact was still valid. It was signed by us, right? So someone could potentially replay that old artifact into our supply chain. And now, how do we know? If we don't have some sort of freshness of guarantee about files, someone could substitute the fixed artifact, right, with the compromised one. And now they have a known compromise they can work with. typically when these things are published, somebody did, reported a bug, some security researcher discovered the issue, it gets published, people know about it. So now there's this known vulnerability in the artifact, and the attacker can compromise that. So you have to make sure that we defend against things like replay attacks, right? So clients have to be able to programmatically recognize when they're been given a replay attack. And this typically means some sort of freshness guarantee. So one example of this is the aforementioned content trust. So in the content trust environment that was created, there were several different keys, including a timestamp key. So the way that it was set up by Docker was you would create with an offline root key tagging keys. So you'd have 2 keys to sign a single container image. The idea being that it's like a nuclear submarine, right? No one person can launch the nuke. You have 2 keys, you have to turn the keys at the same time in order to launch the nuke, right? Same thing here. If someone compromises one of the signing keys, they cannot publish the artifact because it hasn't been signed by the other tagging key. On top of that, we also have the timestamp key, so that, again, for the example I gave moments ago, if we rebuild the image because there was some vulnerability, that can't be replayed. And so they create a timestamp server that sits adjacent to the registry server so that we can validate the freshness of that image. And of course, that's has to be protected so that someone can't compromise that server. Now, people thought, slightly complicated, but the idea is to survive key compromise, right? So that there are issues associated with other ecosystems where keys, you can compromise a single key and do a lot of damage, right? So content trust was built with this idea that we need to be able to survive key compromise. Tough is a framework that allows us to deliver software combining trust, compromise, resilience, which was built into content trust, as I mentioned before, integrity, and freshness. This is a graduated CNCF project. The idea being is that we want update systems to be able to validate the metadata and then install an update. So think about this, like if you have just like Firefox running on your laptop, right? It updates itself periodically. You don't really have any interaction with that other than maybe you have to restart the browser for that to happen, right? But it somehow has to download the new version of Firefox and ensure that it wasn't compromised in some way, right? Frameworks like Tough allow us to do that, where we validate the metadata associated with an update and either pass it or fail it based on whether or not that metadata is valid, and that requires some signatures too. So being able to use these types of frameworks means that we'll be able to do some validation in a programmatic way without having to involve humans, but still achieve the validation that we need for software artifacts. Now, another piece of software that was mentioned in this slide, but we go into it here, is Intoto. So again, I mentioned Justin Kapos before. He was the creator of Intoto. The idea here is to create these documents that describe what the activities are that I mentioned before, right? So a activity is recorded in what's called a link metadata file. That activity, again, could be a Git clone, could be a Docker build, whatever that might be. That is performed by a functionary. That could be a human, right? That could be a CI system performing that step. All of those steps that make up a software build are captured in what's called a layout, right? This is the sequence of steps in the software supply chain and then we require a functionary to sign that as well, right? So we know exactly what are the steps that we need to take in order to build a piece of software, right? We take each individual step, we define it, and we sign it. We verify it before we move on to the next step. Once we complete that step, we take that definition of the second step, we sign it, so on. And we verify in each step. But then we also take the overall set of steps in the layout and we sign that entire thing. Right? This provides guarantees that only the activities that were done during the software build were done and nothing else was done, because we can detect if somebody changes the build, changes the Git repo that was cloned, changes any of those steps, either individually or from the entire layout, right? Because if I'm going to, as an attacker, require that, some other binary gets pulled, right? I have to alter one of those steps, or I have to add a step to the layout. Well, it's not going to exist in the original layout. And so I can validate that no, the steps that I defined that were not taken and should be invalid, right? And then we sign that together with the links and the designated functionaries. And that's all released as part of the final product. And then we can validate that, again, either manually, but ideally via automated tooling. This is the basis of the software framework that I mentioned before, SALSA, which we'll talk about in the next section. But we're going to look at in toto, and you're going to kind of work with it in this lab, because it's an important part to understand how in toto works and how you would perform this kind of validation and how the relationships between the links and the layout work within a software supply chain. So, okay, let's transition to doing that. I'll let you take over here. Oh, I need to close that.
All righty. I see Wiggly Mike's on my receiver here. I see Wiggly Mike on the Zoom here. So I assume folks can hear me. Okay, cool. All right, so in this next lab, we are going to be covering in toto. That's the tool that Chris was just talking about. You can think about it as really extending bureaucracy of having things signed, this time into every single step that you are going to be doing, that you took in order to build some kind of software. And why are we doing this? Well, it's because we want to make sure that if anyone has done any kind of fishy business within our software supply chain, we want to be able to verify that. And we want at least something that can say, hey, there has been some sort of tampering that's occurred. So in toto is one way that we can make it a little bit easier to do that. So in order to get us started, we will be installing in toto. And this is always one of the fun things to do on these lab machines, and that's to install something on pip. That's the Python package manager. Python package manager. Say that several times fast. And so we're going to go ahead and actually install pip after a little bit of sudo apt updating. And you will watch me again as I struggle with all the pieces here. All righty. So then we'll go over to a terminal. All right. I'm already signed in, and I don't have the lab done on this particular machine, but I have it done on another machine. So we're going to go ahead and install pip. We're just going to do the sudo apt update and sudo apt install of the latest Python 3 pip. And that's going to get done in time. Yeah, time. So once that's done, we need to install in toto as a Python, essentially as a Python package. Now, we are going to be passing a rather scary looking option of break system packages. This is something that the latest versions of pip have begun enforcing. They want you to use virtual environments, that fun thing with Python. So we are going to be installing in toto, and we will allegedly allow it to break some system packages. However, we are installing the latest version of in toto that should not overwrite anything and cause us any grief later down the line. And I confirmed that earlier today. So I'm just going to go ahead and grab this command right here. All right, looks like we're all good there. And we will go ahead and pip3 install it. So it's going to go ahead and download all of the dependencies for us. Again, if you're concerned about what the break system packages is supposed to prevent, then by all means, we have a little nota bene here, right here. So as we let that install on my machine here and hopefully on your machines as well. We're then going to take a look at the tools that get installed. So naturally, signing and again, injecting bureaucracy is never an easy thing to do. So why not include several tools that will make that a little bit easier? So we have several things such as, and the ones that we are really going to be using are in toto sign, in toto verify, and in toto run. Sign, of course, to apply signatures to each step of our build process. Verify so that we can, well, verify the signatures, and run so that we can actually produce those documents that will describe exactly what happened and thus give us something that will actually be signable with the in toto keys. Of course, there's a series of other ones here. That's you can read about those down here in the installed list of command line tools. Now, you might be wondering, okay, how do I automate this? This is where you might have, again, some sort of CI worker or some sort of automated server that can, as part of some overall pipeline, actually pull off some sort of script that does that for you. So because it's just a command line, you just really need to, and actually these days, I believe there's a container too. Don't quote me on that, but there should be a container out there, which will make it much easier to prepare a pipeline to actually have a tool like in toto. All right, so next up, we need to have functionaries. These are the ones that will actually, these are going to be authorized programs or really entities that will perform some kind of a supply chain step, the git pull, the Docker build, etc. So in order to do that, we will have to start off with a couple more keys. And this time we are going to be using RSA keys generated through OpenSSL. These are the same types of keys that you potentially do to maybe set up HTTPS upon your websites. So we'll go ahead and install these two. So again, you can go ahead and ignore those scary looking warnings here.
So one of the reasons why we're doing this is because I just want to mention, why are we generating more keys? We had a bunch of GPG keys earlier, right? We had cosign keys. There we go. This is one of the areas where in toto really only supports, and you can see it in the text, certain formats of keys. And there are various formats. Well, one of the things that's not supported is a GPG key, for example. So if we tried to use that, in toto would not be able to use it. So we're in different ecosystems. So we have to we can't use a GPG key. In toto directly doesn't also support cosign. And so we have to create keys for in toto that it can understand, right? So it has to have a particular format. This is where, you know, things aren't complete, right? Where we don't have one ecosystem. We don't have one opinion about keys. And so we're forced to use the keys that will actually work for the system that we want to use.
Yep. So that does introduce a little bit of, well, a bit more complexity to the process. Again, this is somewhat of an emergent technique that's going on. So as time goes on, we will hopefully see much more formalized solutions, something like a cosign type of deal with something like, let's see, supply chain step signing. All right, so we're going to create our functionary. So I wanted to go, turns out I generated it in the wrong directory. So we'll go generate the app build PEM. That's the one for that is the key for the app builder. And then we're going to have yet another one for the pub builder as well. And that should result in 2 keys for us right there. So with that, now we need to actually start creating some attestations. These are going to be essentially statements that say this thing was done. And that's where you would get things like I signed off on this and I signed off on that. Basically, it's sort of covering what kind of things have been done and putting it into a method that's going to do that for us. Let's see. You will need to have the registry container from the previous, you'll want the git daemon container from the previous lab. So if you wanted to run that, then that would be a Docker container run. Git daemon, that would be this one right here. I believe I still have that up and running, but if it did get removed at one point, then by all means, just Control R, look for Docker container run, and look for --name git daemon, and that will get you back up and running on that. All right, we'll do sudo docker ps just to confirm that, yes, my Git daemon is still alive, and that also, if I do a docker logs on said Git daemon, we can see here that it is still indeed alive. All right, so first things first, now we need to actually do something. Now, you might think, okay, let's just do something, and then I have something to sign. Unfortunately, that doesn't really work. We need to make sure that Intoto is actually, aware of that. And that's where Intoto run comes in. Basically, what we're going to feed it is going to be what step of the process we're actually going to do, the signing key, so that's going to be whose signature is going to be attached to this particular action, and then finally the actual action itself, in this case, git clone from our local hello world. So I'll go ahead and do that. I believe I still have my old Git address here, and there we go. I am just going to grit my teeth through that and go there. Okay, cool. Oh, that's incorrect. Awesome. All right. So going back here, Control C. There we go. And Control C. And Control C. There we go. There we go. All right. So I am going to tell it to Intoto run. All right. And so what this should lead to, and let's see here. Let's see. I need to have my export. And Control R, Control R. There you go. All right, try that again. Sorry about that. There you go. So that should have cloned us over. Turns out I didn't have my Git address there, but that should clone us over there. And now we have our VCS right there. Okay. Hopefully it doesn't bite me later. We'll see. All right, so we'll go ahead and cat that link right there. So what's been produced is this thing, this artifact known as a link. That's a link in the chain of this software supply chain. Funny how that worked out, right? Okay, so we've got that set up there, and we can see that it has indeed been associated with a particular action. So now we have the link file generated. Okay. So in here, if you wanted a breakdown of what exactly had happened here, Intoto is going to wrap the git clone command. It's going to hash out the contents of the source code, add that hash together to generate the metadata necessary. Then after that, sign that metadata file, which you can potentially push up to some sort of central service, like that Graphias tool I was talking about earlier. Okay, so within that link file, you're going to have a variety of things. You'll have signatures and who signed it. You've also got the command, of course, to help you validate what exactly had been done. You've got the execution environment. Where did that occur? The names of the files that have been used in that particular link. And of course, you'll have the name of the link, which you defined in the Intoto run. And then finally, you've got the products that was what was actually produced by that. And so if we take a look here, we see here that that's what was created there. Actually, you know what? I'm going to go ahead and actually remove. Yeah, I'm just going to remove my VCS. I'm a little bit concerned that maybe I didn't. Yeah, well, RM DRF on hello world. And I'll just have Intoto run do that again for me. There we go. There we go. So now if I take a look, and we can see that, okay, it was still the same thing. Just wanted to make sure. Okay, so now, yeah, go ahead.
I was to say, this step doesn't really produce any products, right? We're just cloning a repo, so we're not like generating anything. You can add more details to this. Like if you wanted to specify what materials were in the repo and say what's valid, what's not, you can get down to the minutia of the repo and say, this is allowed to be in the repo, this isn't. We didn't go to that detail here, but you can.
Yep. And that's what these options down here are explaining. So how far do you want to go down? And who's going to really have that say? Honestly, it usually boils down to what is the policy that's currently being enforced by your company, your enterprise, etc. So now, in that case right here, now let's go add yet another link. And this is still going to be within the purview of the app builder functionary. And this time, we are now going to do an actual build, or rather just a Docker container run, really. And so in this case, we're going to call a new step called build one. We'll give it a timeout of about, what is that, like 3 minutes? Yeah, 3 minutes, I think. No, more than that. Yeah. So, sorry about that. 5 minutes. Yeah, there we go. Almost. No, not 5 minutes. 3 minutes. Yeah. Yeah, 3 minutes. Okay. We're also going to produce the materials. So that's going to be the contents of Hello World. All of those will be included in the file. Next are the products. So what exactly will get created? Then we're going to record the streams, followed by the big old command that's going to run the container and ultimately perform the step, which is going to be running a container and then having a series of go commands. So we'll go ahead and grab that command right there, big old command, pop that in, and now we will let it run. So this is going to continue running, and this will produce yet another step, yet another link, excuse me, in this chain here. This might take a little bit. So while we wait for it to go through, let's go see what we're going to expect. So now we've got the initial VCS, that's the clone, and then we've got our build right here. This one is going to be the one that was just produced, and we'll compare again while we wait for this to finish up. We will compare what the contents will be, but this link file will likewise have signatures indicating who done it, essentially, who is it signed by, what were the byproducts. So in this case, it's just a standard error output, no standard out. What was the command? So this was the big old command that we actually passed in that large brick of CLI. We've got the environment, which don't really have anything, but we do have the materials, which would include things like the README that we created and the main.go. And potentially if you had things like the, let's see, if you had the, what was it, the git ignore, yeah. If it was in there too, that would have been there as well. And then after, yeah.
I just wanted to add, one of the reasons why we didn't restrict the inputs is because we don't know what you all committed, right? So in the lab, we had you commit several files, but you could have committed anything. And if we restricted the input, then this would fail because we're saying that we're restricting the inputs of the repo to X files, but you could have committed whatever you wanted in your own VMs, right? That could be a git ignore. You could have just made random files and touched them and committed them as you were kind of playing around in the earlier lab. So we didn't want to restrict that and like have things blow up. Yeah. So
yeah, nothing funner than a lab blowing up live on stage there. All right, so at this point then, I believe mine has finished, and it does mux up your terminal a little bit. So just press a couple of enters and you should be back together. And now we have our build there. Let's go take a quick look at the build link right there. And we can see that we've got the same sort of byproduct, which was really just a big brick of standard error right there. So that's been completed there. Yeah, we can see here, I created a git ignore, and you can see that that's there. All right, so at this point now we've got two individual links. The thing is they haven't been associated with each other, or rather chained together. So in this next one, we are now going to go ahead and chain these links together. And so this is where things are going to get a little bit tricky here, because first off, we need to gather a couple of things. We need to gather the signature key ID, which is something that's actually been carried throughout our entire in toto run. So we want this value right here, which is the result of cat vcs1.link. You don't have to worry about JQ. That they actually started including that in the latest Ubuntu cloud images, which is quite nice. All right, so you cat this link, and you want to go ahead and, just to make this easier, take this string and maybe put it in a notepad or something. I created a template for myself a little bit later, but you will need this value later. This is essentially the functionary's signature key ID. Next, we need to get a single string for the contents of their key or signing key, and that's going to be provided by the second command down here. It's going to be just one really big string there, like so, right? So we're going to go ahead and pop that in there, and you can see that you've got this, again, big brick of command line output. Okay, now that that is complete, let's go ahead and prepare that really tricky file. So this is the tricky file. This is the root layout. This is the document that is ultimately going to link chain our two links together. And so what we need to include is, first off, we need to include the signing keys IDs. So that's the output of the first one. And so we're going to replace that in three different, we're going to replace that in three different parts of this document: the pub keys, the key ID, and then this string right here under keys right here. So I'm going to go ahead and do that. And so one easy way that you can do this is the foam. All right, so, and this is going to be super tricky. Let's make sure. All right, so we're going to vim our root layout. All right, so I'm going to paste that in there right now. And so what I need to remove are the following things. I need to basically remove, oops, darn it. All right, there we go. I'm gonna remove a bunch of this stuff right here. So I'm sure there's a better way I can do this. And yeah, there we go. All right, so going to remove this whole public key business right there and just put a quote just there. So like that. We're going to fill that in later. Also going to remove this this bit right here. So all right, so let's see. You're seeing my Vim noobiness here. All right, we'll remove that right there. We will also remove this part right here. Again, I know there's a faster way to do it in Vim. I'm sorry. So we'll go ahead and remove that right there. So this will be our file here, like so. Okay, I'm gonna write that real quick, and I need to grab this value right here without the quotes. I'll open my root layout again, and I need to put it under or in between here. Next, I need to put it in between here, and I need to put that right there. Okay, so that's the first part. That's the key ID for our functionary. Next, I need to grab this big old block of CLI. If this would let me. Hey, come on. Yeah. Oh, geez. Sorry, folks. All right, so. There we go. Grab it. Okay, cool. Oh, there we go. All right, cool. So now I got that. And under between the quotes here on public, I'm just going to grab that entire string right there. And so those are the replacements you need to make. Please be careful about making these. It does get a little bit tricky. I usually just pull this document out into a notepad, make my edits, and then pop it in. So assuming I got everything correct. And so inside of this root layout, we have a lot of things going on. We have the signatures and the signees, of course. And inside the sign section, that's going to state the various details, such as when, what kind of signature is it, when does it expire, various readmes, and what steps it actually applies for. We'll also have a list of optional inspections, and of course, the keys that were involved for that particular step. Next, we're also going to have, and then each of these steps are going to include things like the expected materials, expected products, the public keys involved, and of course, the expected command as well. So now what we're going to do is we're going to create another key, yet another key, always another key. So we will create yet another key. This one is going to be for the chain root. So we're going to actually have a different signee for the root layout there. And then we're going to do this one right here. Okay, there we go. All right, there we go. Okay, so we're going to create those. We should have the two chain root pubs there. And now we're going to go ahead and sign that root layout that we just created. And we're going to create a brand new file called rootlayout.sig. All right, so we grab that here, pop that, and assuming I got everything correct, this should work. Yes, it did work. Excellent. Okay, great. Again, always finicky with that. Just be careful about what you are replacing. So now I should now have a, root layout sig, and this is the signed layout here. So now if we do some more on that on layout.sig, now we have a little bit more details. Again, it's the same kind of deal, except now we do have a signature that has been applied to this root layout. This was actually not initially there when we did the file initially. All right, so our root layout has been signed, and now you can see in here, you're going to see that the two steps, the one that is the hello world clone and then the build, those are now going to be in the layout. So we're going to go ahead and verify our chain. And with this, we're just going to use the in toto verify. We'll be verifying using the chain root public key that we just created. So we'll exit out of that, do the in toto verify. And then we can see here that everything has been, everything is looking okay here. And if there were any complaints, then we would have seen it, things like, oh, this particular step doesn't match the previous signed version. All right, so supply chain is intact. It's accounted for, or rather attested for. Now let's do a little bit of tomfoolery, so to speak. So let's go attack the supply chain. We are going to go ahead and change things up. So we are going to make the VCS1 step actually clone something else. We started off with our hello world. Now we're going to pull in a little host info type of server there. So we'll go ahead. We'll use in toto run for that, by the way. So in toto run. So no errors. And we should have a new VCS. Yep. But let's go see what happens if we try to verify it again. All right, so we'll do a Control R, verify. All right. Yeah. All right, and we can see here that there's a little bit of a complaint here. It says it did pass all verifications, but a little bit of a complaint. That's a good sign. It means that regardless of what someone tries to do, even with our keys, if they try to interfere with our supply chain, we can see here that there is some sort of, well, fishy business going on. All right, so that's one way, and that's assuming that folks actually have access to your keys and such. But what if they had access to the link files themselves? So what I'm going to do is a little bit of, again, some more tomfoolery there. And we will do grab that. All right, and so what we will do is we'll go try to bring it back. So let's go see what happens here. We're going to try and realign it with the previous correct repo. WQ that. Oops, nope. Okay. Oh, right, I'm in Yano. All right, Control X, Y, Z. All right, there you go. So then, verify. Let's go see if we verify it again. Here now, we actually tampered with one of the files, and we can see here that this one did not pass the verification. Now we can see here that, hey, one of our links is not correct, and that is how in toto is going to be able to help protect you from a supply chain breach. All right, were there any questions? Thank you. All right, hand it back to you, Chris.
So a couple things I want to point out is one is like we talked about the two keys to launch the missile, right? And that's exactly what happened there, which was we had one functionary which was responsible for signing the link file, and we had a separate functionary responsible for signing the layout, right? That way, if we have survivable key compromise, right? So even if a key is compromised, we can't actually deploy the software because the layout invalidates the link, right? So if our functionary's key is compromised and the link file is altered and signed by that functionary, it doesn't match the layout, right? We messed with the very end, we messed with the file itself trying to change what we actually cloned, right? Well, this is not what we cloned. That's not what we signed, what we cloned, right? Because what we signed, what we cloned was the GitHub repo, whatever it was, trash levels or hello world or whatever it was up here, right? So we didn't, even though we tried to manipulate it and trick the system, the layout file invalidates our link file, and therefore would then fail to build, right? So we've got survivable key compromise. We have detection. We know that if we have somebody trying to, as Christian said, try some tomfoolery in our software supply chain, that it's going to be detected through the use of these link files and the cryptographic signing that we've used, right? There's something else I wanted to point out. Oh, this here. So one of the nice features of Intoto is the fact that we are distributing the public key for verification with the files themselves, right? So our layout here has the public key, right? He did a bunch of edits to embed that into the file so that it could be distributed with the actual metadata. And so now we don't have to have two distribution mechanisms, one for the public key, one for the metadata. It's all together. Now, in our case, we're kind of statically putting this together so you can see manually how you would do this. There are facilities for retrieving these things dynamically, right? So you can have a KMS, let's say, that you store keys in, and you can tell Intoto, for example, to go get that key associated with that layout, rather than having to like paste these things in manually. But the more automation there is, the more abstraction there is. And so we wanted you to see exactly what the automation will be doing, which is relating all of the keys to the actual metadata so that they're, you kind of do that manually. So we make you do it the hard way, because that way, if you use these types of tools and they're automated, you understand what they're actually doing under the covers, right? So we try and do that in a lot of cases. So I wanted to wrap this up with a conclusion about security frameworks. And I've mentioned Salsa at least once, and Fresca as well. And we also need to talk about the secure consumption framework. The idea is that we're all on this journey together, and it's not an all or nothing proposition. It's an iterative process of improvement. But we need to be able to communicate that to each other. In order to do that, we have to have a common language, right? Let's think of something like the OSI, right? If you're familiar with the OSI in here, right? The layers of networking, right? It's a common framework for us to talk about networking in general, right? I can say this is a layer 7 load balancer, and you know what I mean because we all understand the OSI model, right? I can say this is layer 3, layer 4 networking, and you understand that, right? So this is all of this stuff combined. We need this common language to talk about it, right? So we have a number of different threats to integrity, right? Bad code gets submitted either by accident or by somebody who intends to do something malicious, compromised source code, modifications to code, bad dependencies. The build platform itself can be compromised. We can bypass the CI or CD systems to try and deploy software that, or build software that's compromised. We can even compromise the package repository itself, right? Attack the artifact directly and replace it with something different, or do a replay attack. Use bad packages, right? So the mitigation is all of these things that we've been talking about, but in order to communicate that, we want to talk in terms of how well we're doing, where we are in our journey, how we're progressing. And Salsa is a framework for communicating software supply chain integrity for producers. And then there's another framework for talking about consuming software, so we can talk about how well we're doing, how advanced we are in consuming software. So SALSA stands for Supply Chain Levels for Software Artifacts. This is that framework that covers supply chain vulnerabilities, right? You can think of it as just like a checklist of standards and controls for where we're at in our maturity in our build systems, right? The idea is to help producers protect their goods from tampering and any sort of compromise. Consumers can then verify those goods, and we can rely on those things to be secure depending on how mature the producer is. And infrastructure providers can harden their platforms and can communicate that to consumers, right? Especially if we're using a managed service and say, we have this much maturity in our system, and you can then have more trust in the systems that we're offering. SALSA is then part of the, again, the Open Source Security Foundation, the OpenSSF that I mentioned before, and is a framework that's defined by a number of different vendors that supply software and want to, of course, safeguard artifact integrity. So within the language of the framework, right, we've talked about things like artifacts, right? Artifact can be anything, libraries, dependencies. It's really just within the framework here, it's an immutable blob of data that we're going to deploy somewhere. Attestations, as we saw, are authenticated metadata about artifacts. We just produced those within Toto, right? We know exactly what activities were performed because we defined them, we signed them, and we can detect if they're in any way altered. Sources are unmodified artifacts that were directly authored or reviewed by some sort of entity, right? So really the farthest upstream point in the supply chain. A build is what you think it is, right? We're going to take the raw inputs and create some output artifacts, typically some software. And the package is then the artifact that's published. Again, this is the output of the build process, just generically an abstraction term for, could be a container image, could be a binary, could be a jar file, whatever it is. And then dependencies, again, similar or familiar language here, right? Some sort of input into the build process. Now, in addition to that, we define terms like producer, right? We have somebody who is creating and providing software to some downstream consumer. Verifiers, which are parties that inspect the provenance of a artifact, and an infrastructure provider, essentially a platform provider that provides a build platform of other infrastructure that's associated with build infrastructure. SALSA is broken up into different tracks. So yeah, I know. I was looking. This is sort of out of order. So, because the next slide talks about tracks, but the idea is that we may be good at one thing, but not good at some other part of software deployment. So they broke it up into what are called tracks, which are ways for us to communicate how good we are at some aspect of this. The first track that was created was build, because build is the thing that requires the most attention right now. It was the most important thing to try and generate improvement around, right? So what we're measuring with the build track is the platform that produces the software, which includes the infrastructure that's going to build that software, right? So we have some sort of control plane that orchestrates parts of the platform. Now, in some cases, depending on maturity, this could be just a Docker instance running on your laptop. That's perfectly fine. That's the, Docker engine then becomes the control plane that orchestrates the build. But there are lots of problems with that being the primary build engine for building artifacts, because there are a lot of ways that can be compromised, as opposed to a fully automated, fully hosted environment. Let's say like GitHub Actions, for example, right? I can define steps in GitHub Actions and build software. I can do that with Google Code Build, right? And that's more secure than just Docker running on my laptop. But those are both legitimate ways that we build software. And so they're included in the language of a framework like this to understand like how good is one build versus another and how we communicate that to each other, right? Of course, everything here uses attestations, and that's what gives us the provenance, right? Because we need to, with a tool like in Toto, and the standard right now for attestations in the SALSA framework is in Toto. So there's a reason why we chose that, to show you that. It may it may drift at some point and change from the in Toto format, but right now in toto is the format that is used for build attestations in the framework for producing metadata and verifying metadata. And so within a track, we have different levels. And this is how we define how mature we are when it comes to our practices, right? A level is some sort of guarantee, right? Provenance exists. Builds are hardened. What do those things mean? There's a lot of details about a particular build level, but for example, build level 0 has 0 requirements. So if you've ever built a piece of software and never thought about the security of it, congratulations, you've achieved SLSA build level 0, right? That's how we communicate with each other. I can say, we built the Git daemon today. I built that in a way that was SLSA level 0. You know that it's completely insecure because I told you that's a SLSA level 0 build, right? Because I didn't provide you any guarantees of any of the any of the materials or anything that we built, as opposed to the thing that we just did within Toto. If we like completed that build all the way to the end, I can tell you that provenance exists, right? Because it shows us how the package was built. Does it need to be signed? No. I just have to provide it to you, right? And so I can say that that build, had we completed the entire part of that build and gone through all of the different phases of the build within Toto, we didn't do that because it gets really complicated, was a build level 1, because you just participated in creating something that was SLSA level 1 because you can provide provenance about how those artifacts were built, right? It gets more complicated from there. Build level 2, we have to sign it. And we have to host it by a build platform, which means that it can't be Docker running on my laptop. But I can achieve build level 1 by creating an artifact with Docker build on my laptop, because I can generate provenance on my laptop. And I've done that, right, in the past. But in order to get level 2, I have to use some remote system that I don't have here, right? That can be, again, GitHub Actions, Google Code Build, AWS Elastic Beanstalk, or any other build tools, Jenkins or something like that. It has to be some sort of hosted platform that we can then, at level 3, harden it. Now, of course, this is the most challenging part of something like SLSA, which is if I say that I built an artifact with SLSA build level 3, what I'm saying is I can guarantee unfalsifiable provenance. Right? There's no way that any phase of the build process can be compromised and the artifact will still be built and distributed via container registry or whatever artifact server we're using, right? So it's aspirational. There are currently only 2 systems that achieve SLSA build level 3, and that is the aforementioned GitHub Actions and Google Code Build. That's it. Everybody else in the world can't achieve build level 3 yet. They're trying, but they're not there yet. So now we have a way to communicate. If you're using a service like Elastic Beanstalk, you're using something less than build level 3. I don't know exactly where they're at, but now we can communicate with each other about how artifacts were built and how secure they are, right? Now, how do we consume these things? Well, guess what? There's a framework for that too, right? Because understanding about how we're consuming software artifacts, if we're consuming them securely, because just because a producer produces attestations and signs them, doesn't mean I ever have to look at them, right? I could go, let's say my software producer gives me attestations, gives me an SBOM, signs everything, stores it in an OCI registry, and what do? Docker pull whatever the image is. Did I consume that securely? I didn't. I just pulled the image. I don't care about the attestations. I didn't verify the signatures, right? It's still possible for me as a consumer to consume insecurely. So the secure supply chain consumption framework rolls right off the tongue. is a way for us to communicate how we're consuming software in a secure way, right? And so there's three core concepts, right? Controlling artifact inputs, right? So following a uniform process for consuming open source software. Continuous process improvement, so emphasis on understanding what changes in the threat landscape and evaluating controls that adapt to those changes, because attackers don't just stick to one mode of attack and repeat that over and over, right? They're constantly adapting to try and work around what we're doing, right? It's an arms race. So we need to have process improvement. And then, of course, scale. The idea is that we need to deploy software at scale for large organizations. And so we need to be able to do all this verification and consumption of artifacts at scale. And so you can see the 8 best practices here shown from the infographic, right? Being able to audit how we're doing scanning for vulnerabilities, making sure that we're verifying attestations and signatures, right? So we'll talk about some of the levels that are associated with S2C 2F. So just like Salsa, right? We have levels, right? Level 1, using a package caching solution, performing some sort of inventory of the open source software, right? Actually understanding what's in the SBOM and trying to improve security. Level 2 is shifting security further left by improving the configuration security, decreasing patch response time so that we're patching more frequently when new CVEs come out, making sure that we try and automate that and speed it up as much as possible. Level 3, performing security analysis proactively. Again, this is to adapt to new attacks. And level 4 then is really, again, considered aspirational. And this is rebuilding open source software on trusted build infrastructure. In other words, not relying upon pre-built dependencies, but rebuilding everything ourselves to make sure that we trust that we built everything and we don't have to worry about provenance because we supply our own provenance, right? Now, a lot of this, again, comes with the, you have to think of it in terms of risk, right? Do I need to be level 4? Well, how much risk is involved? I may not need to be level 4. So here are the details of each level, right? Using package managers, local copies of artifacts, scanning for known vulnerabilities, right? Using things like Trivy and other types of scanners for vulnerabilities. Looking for software licenses, making sure we're in license compliance, because part of software consumption is also understanding that we're not violating some sort of license. Scanning in level 2 includes things end of life, understanding incident response plans. Again, as an individual, you may not be responsible for these things, but understanding like where an organization is that you're a part of or that is consuming software helps us communicate. Validating open source integrity. Level 3 then is zero-day detection. So things like deny lists, scanning for malware, proactive security reviews, again, for adapting to how the attackers are adapting. And then 4, again, is really advanced, validating SBOMs, rebuilding open source software, digitally signing rebuilt open source software. So even though we're bringing it in and rebuilding it, we're signing it again so that our own software supply chain doesn't get compromised. And so with those things in mind, hopefully you have a vocabulary for understanding where we're going. Because again, none of this is complete. And, I don't know that it will ever be totally complete. We always have to adapt to new attacks, new methods of people trying to compromise software. But hopefully you know a little bit more about using cryptography to make sure that software that you consume or that you produce can be done so securely. So I do have to do a couple of different things. So one is Promote AI Day here is 2025. I think the date I think it's in January. I'm not sure, but I have to double check with Ron. I know he wanted to promote this. They'll probably also promote it if you're going to the next track, which leads me to the next one, which is the thought leadership track. This is from 9 p.m. Sorry, until 9 p.m. This is over at 101 Townsend. So it's kind of straight down Embarcadero, make a right on Townsend, go to 101 and to the Cloudflare building. And they've got a number of different talks on, one of the ones I'm looking forward to is actually quantum computing and its threats to cryptography, because again, we looked at like attacks when it comes to, in the first section, when it comes to cryptography, and it's really about how long does a normal computer take to break these ciphers, and you get a quantum computer and all bets are off. So hopefully we'll hear some more about that because of the power of quantum computing. Anyways, thanks, folks. I think that is, yeah, that's the last slide. So thank you very much. I appreciate you guys coming. And hopefully we'll see you over down at Cloudflare. Thanks, Ron. Thanks, Google. Thanks, everyone. Put all this together for us. And thank all of you, too, for sticking around. I believe we have certificates lined up for a lot of you that are still here. So and we have the one more. Yeah, we do have the one more. So I'm gonna switch off. Let me unmute myself here. Okay, so I'm gonna stop the share. I think if Carl's still there, we're all good here.
Yeah, thanks, Carl.
Appreciate it.
Didn't see any questions online, so I think we're good.
Yeah,
Thank you very much.
Carl also mentioned the next track will be streamed as well. Any other closing remarks, Carl, that
No,
you might have? Okay.
other than thank you.
All right.
Thank you so
thanks,
much.
Carl. All right. Thanks, everyone.